localized bursts of star formation, while in others the energy input is so intense that it disperses clouds before they can collapse. The result is a galaxy where stellar birth and stellar suppression are written side by side along the same cosmic tracks, all orchestrated by the central engine. This duality, jets as both creators and destroyers, makes IC 5063 a compelling case study for the larger question of how black holes shape the fate of galaxies. The sight of luminous rails of gas aligned with the jet beams gives this galaxy a unique appearance among active galaxies. It is as though the black hole has laid down scaffolding across its stellar city, forcing the interstellar medium to reorganize around its energetic will. In the grand cosmic picture, IC 5063 demonstrates that black holes are not silent sinkholes but dynamic engines whose feedback determines how galaxies evolve. They etch their influence not just in the invisible realm of gravity but in radiant tracks of matter that remain as signatures of their presence across cosmic time. Astronomers investigating IC 5063 use the full arsenal of modern instruments to disentangle the complex physics of jet-gas interactions. Observations with the Atacama Large Millimeter/Submillimeter Array, ALMA, have revealed streams of cold molecular gas being accelerated to hundreds of kilometers per second along the path of the jets. This is striking because molecular clouds are typically fragile. The fact that they can survive such extreme turbulence suggests that magnetic fields or dense clumping may shield them from total destruction. The jets appear to entrain this cold material, dragging it outward like cargo on invisible rails of plasma, and reshaping the galaxy's gas reservoir on galactic scales. Infrared imaging with the Hubble Space Telescope and spectroscopic data from instruments such as MUSE on the Very Large Telescope, VLT, have added another dimension, showing shocked ionized gas that glows brightly where the jets slam into denser regions. These signatures trace out shock fronts propagating through the interstellar medium, heating it to temperatures of millions of degrees and producing X-ray emission observable with space telescopes like Chandra. This multi-wavelength portrait reveals not a single uniform jet, but a layered system where relativistic plasma, hot ionized gas, and cold molecular clouds interact in a chaotic feedback loop. From a theoretical standpoint, IC 5063 is invaluable for testing models of AGN feedback, the process by which active galactic nuclei influence the fate of their host galaxies. Cosmological simulations require some form of feedback to explain why massive galaxies do not endlessly form stars, and why the largest galaxies are observed to be quenched. IC 5063 provides an observational anchor. Here, feedback is visible in action, with jets clearing channels through the galactic disk, altering gas dynamics, and regulating star formation. By comparing the spatial distribution of stars, gas, and radiation in IC 5063 with simulations, researchers can refine the mechanisms that govern galaxy evolution across billions of years. There is also growing interest in whether the jets can induce positive feedback, triggering new stars rather than suppressing them. Some regions near the jet paths show enhanced star-forming activity, consistent with shock-compressed clouds collapsing more quickly. This dual role, destructive along some routes, creative along others, complicates the picture of black hole feedback but also enriches it. In IC 5063, the balance between quenching and triggering appears to depend on local conditions, gas density, and the orientation of the jets relative to the galactic plane. Looking forward, IC 5063 will continue to serve as a natural testbed for high-resolution numerical simulations of jet-driven outflows. Future instruments like the James Webb Space Telescope and the Square Kilometre Array will allow researchers to probe even finer details of the molecular gas kinematics and magnetic field structures, offering a clearer view of how energy from a supermassive black hole can ripple outward to reshape an entire galaxy. In many ways, IC 5063 is not just a galaxy, it is a cosmic experiment, unfolding on scales so vast that only light from distant epochs allows us to witness the results. Numerical simulations of IC 5063 have become essential for bridging observation and theory. Hydrodynamic and magnetohydrodynamic (MHD) models attempt to reproduce how relativistic jets carve their way through clumpy, rotating disks of gas. These simulations show that when jets encounter a porous medium filled with dense molecular clouds, they do not simply pass through like drills. Instead, they deflect, fragment, and weave around obstacles, generating networks of shocks that ripple throughout the galaxy. In IC 5063, this process creates the illusion of straight rails, but on smaller scales the structure is far more turbulent, with gas being accelerated in multiple directions and at different velocities. Magnetic fields add another level of complexity. They act as invisible scaffolding that can either resist or channel the motion of ionized gas. Simulations suggest that strong magnetic fields in the disk of IC 5063 may stabilize molecular clouds long enough for them to survive jet impact, allowing cold gas to persist in an environment that should otherwise shred it apart. This persistence is critical, because it maintains the raw material for potential star formation even as the jets are energetically heating and dispersing the surrounding medium. In this way, IC 5063 challenges the simplified assumption that feedback is purely destructive. Its rails of jet-driven gas are simultaneously conveyors of turbulence and guardians of star-forming matter. Observations also reveal velocity gradients that align almost perfectly with the jets, indicating that entrainment is not just a side effect but a dominant process. Gas along these rails is accelerated to hundreds of kilometers per second, with evidence of multiphase outflows, hot plasma streaming outward, warm ionized filaments glowing in optical lines, and cold molecular gas clinging to the jet edges. Together they form a stratified outflow system, each layer responding differently to the same central engine. This multi-phase structure has become a central focus of research, because it may represent a universal blueprint for how black holes regulate their host galaxies across cosmic time. IC 5063 also provides a key opportunity to compare radio-loud and radio-quiet AGN feedback. While many active galaxies show winds driven by radiation pressure, IC 5063 is dominated by mechanical feedback from jets. Studying its rails of energy allows astrophysicists to quantify how much mass, momentum, and energy are injected into the galaxy by mechanical processes compared to radiative ones. Results so far suggest that jets can be more efficient at stirring and redistributing gas than radiation alone, especially in galaxies with dense, gas-rich disks. As telescopes push to higher sensitivity and resolution, scientists expect to trace the smallest filaments of jet-gas interaction in IC 5063, possibly down to the scale where individual star-forming cores are being compressed or destroyed. With JWST's infrared vision, researchers hope to detect young stars forming along the jet corridors, testing the hypothesis of jet-induced starbursts directly. Meanwhile, the upcoming square-kilometer array will map the radio emission of the jets and their cocooning plasma bubbles in unprecedented detail, giving insight into how these rails expand, evolve, and fade over millions of years. IC 5063 thus stands as a live experiment in cosmic engineering, where a black hole. In the broader context of cosmic evolution, IC 5063 offers a window into how galaxies transition across different phases of their lifetimes. Cosmological simulations predict that without feedback from supermassive black holes, large galaxies would accumulate too much cold gas and produce stars at unsustainable rates. The result would be a universe crowded with hyperluminous galaxies, inconsistent with what telescopes actually see. IC 5063 provides tangible evidence that feedback through jets is one of the regulators that prevent this runaway growth. Its rails demonstrate a mechanism capable of redistributing gas, heating it, or ejecting it into intergalactic space, ultimately throttling star formation and pushing the galaxy toward quiescence. The role of IC 5063 in cosmological models is particularly important because it bridges two extremes: On one hand, the quasar winds seen in high-redshift galaxies that sweep out interstellar gas in massive blasts, and on the other hand, the quieter low-luminosity AGN that only subtly stir their environments. IC 5063 shows that even intermediate-powered jets can dramatically reshape a galaxy if they intersect with a dense disk. This suggests that the efficiency of AGN feedback is not purely about the luminosity of the black hole, but about geometry, environment, and the fine structure of the interstellar medium. In essence, the rails of IC 5063 are cosmic signatures of how orientation and context amplify the influence of a black hole. The energy injected along these corridors also leaks beyond the galaxy itself. Outflows traced in X-rays and radio extend into the circumgalactic medium, where they mix with infalling material from the cosmic web. By stirring this reservoir, the jets may regulate not only the internal star formation of IC 5063 but also the exchange of matter between the galaxy and its larger-scale environment. This interplay between internal processes and cosmic structure is a key ingredient in understanding the coevolution of galaxies and their central black holes across billions of years. In the grand hierarchy of structure formation, galaxies like IC 5063 serve as nodes where gravity, radiation, plasma, and turbulence converge. The rails cut by its jets are temporary scars. Over tens of millions of years, they will dissipate, leaving behind altered distributions of stars and gas. Yet their significance extends to cosmological scales, because they reveal how the feedback loop operates. Black holes grow by consuming matter, they then unleash jets and winds. These outflows sculpt the galaxy, and the reshaped galaxy in turn controls how much more matter the black hole can consume. IC 5063 embodies this cycle in visible detail, providing a snapshot of the universe's self-regulation at work. Seen through a philosophical lens, IC 5063 becomes more than just an astrophysical case study. It becomes a metaphor for the deep paradox at the heart of the cosmos, destruction as a prerequisite for creation. The rails carved by its jets embody the tension between order and chaos, stability and disruption. They are scars, yet they glow with energy, as though the act of being torn apart also produces beauty and light. This duality reflects a fundamental law of cosmic evolution. Galaxies, stars, and even life itself are sustained by cycles in which dissolution is inseparable from renewal. The black hole at the center of IC 5063, often imagined as a devourer of matter and light, reveals itself here as an architect. Its jets, violent and uncompromising, dictate the geometry of the galaxy's future, laying invisible tracks that channel the flow of gas and determine where stars may or may not emerge. In this sense, the rails are more than plasma corridors. They are blueprints of destiny, written not in ink but in relativistic particles. They remind us that creation in the universe does not happen in a vacuum of peace but amid the storm of opposing forces. The imagery of rails also evokes the idea of guidance, of a path set down across the vastness of space. Just as railway tracks constrain movement along a fixed direction, the jets force the interstellar medium into patterns it would not have taken on its own. This echoes a deeper truth about cosmic history. While randomness abounds, structures emerge because energy follows channels, fields impose order, and gravity sculpts chaos into symmetry. IC 5063 is a living diagram of this principle, randomness bent into rails of coherence. There is also a lesson about impermanence. The rails will not last forever. In millions of years they will fade, the gas will disperse, and the galaxy will assume a different form. Yet the traces of the event will remain embedded in its stellar populations, its gas distributions, and perhaps in new generations of stars born along those luminous scars. In this way, IC 5063 mirrors the human condition. Our lives too are shaped by intense events that leave imprints, sometimes destructive, sometimes creative, but always transformative. To look at IC 5063 is to see the universe telling us that growth requires disruption, that harmony emerges from turbulence, and that even the most violent forces can carve paths toward renewal. It is not just a galaxy, it is a cosmic parable written in light, rails, and darkness. If one allows IC 5063 to be read not only as an astrophysical object but also as a symbolic reflection of consciousness, the rails of its jets take on the character of thought itself. Just as the black hole channels its immense, invisible energy into narrow corridors of light and plasma, the human mind channels the vast ocean of potential experiences into specific patterns of perception, intention, and meaning. The jets become metaphors for focused attention, carving paths through the chaotic gas of possibility, leaving behind illuminated tracks that show where energy has flowed. Consciousness, like the galaxy, is not static but sculpted by turbulence. Thoughts collide, reorganize, and are sometimes torn apart, just as clouds of gas are shocked and compressed along the rails. Yet within this storm, structure emerges, a coherent identity, a trajectory of growth, a history written in patterns. IC 5063 shows that order does not come in spite of disruption but through it, and the rails remind us that clarity is often born in the aftermath of intensity. The black hole itself becomes a metaphor for the deep, unobservable core of awareness, the silent center that neither light nor matter can escape, yet from which streams of transformative energy are launched. In the same way, consciousness springs from a hidden depth beyond words or images, projecting creative forces outward into experience. The jets that stretch across the galaxy are like intentions radiating from this inner singularity, shaping the landscape of a life. In this interpretation, the impermanence of the rails is also significant. The paths of thought, like the luminous tracks in IC 5063, do not last forever. They fade, disperse, and are replaced by new currents of energy. Yet their imprint lingers, guiding what comes next, weaving memory into the evolving structure of the self. The galaxy becomes a mirror of the psyche, scars of the past and the radiant potential of the future coexist in every moment. IC 5063 thus illustrates a cosmic resonance between matter and mind. The rails in space can be read as the rails of consciousness, luminous, transient pathways where energy finds direction, shaping both galaxies and lives. To contemplate them is to see that we, too, are sculpted by invisible forces, and that the lines we carve in thought ripple outward into the architecture of our worlds. If we extend the metaphor further, IC 5063 becomes not just a symbol for individual consciousness but a fragment of a greater cosmic mind. Its rails of plasma can be imagined as neural pathways within a universe that thinks, where galaxies are like glowing synapses in an infinite brain. Just as our neurons fire electrical impulses that etch temporary traces across networks of memory, the jets of IC 5063 inscribe momentary tracks into the interstellar medium, lines of energy that shape the galaxy's unfolding story. In this vision, the cosmos is not inert matter governed only by blind mechanics, but a living system of self-organization and feedback. Black holes, far from being dead ends, become engines of thought, singular cores that absorb information, compress it beyond recognition, and then radiate influence outward through jets and winds. Their rails resemble the firing of synaptic currents, energy sculpting matter into ordered configurations. IC 5063, with its luminous scaffolding of rails, could be read as one of countless thoughts expressed by the universe, fleeting yet significant, local yet connected to the whole. When seen this way, galaxies are not separate objects but patterns in a cosmic tapestry of cognition. The cosmic web itself, with its filaments stretching across billions of light-years, becomes the architecture of a grand mind, where every galaxy contributes its unique voice. IC 5063's rails, then, are not just scars of violence, but phrases in the language of the universe, messages written in light, turbulence, and gas. They speak of the balance between creation and destruction, of the necessity of chaos in giving rise to form, of the cycles that unite all scales of existence. For human beings, contemplating IC 5063 in this framework awakens a sense of kinship. Our thoughts, too, leave trails that ripple through our environment, influencing the future long after the moment of their birth. Just as the galaxy's jets shape where stars can form, our intentions shape where meaning can take root in our lives and societies. The rails in IC 5063 remind us that consciousness is not separate from the cosmos but a microcosmic reflection of it, the universe gazing into itself through countless luminous pathways, from galactic rails to human minds. In the end, IC 5063 is both object and metaphor, a galaxy of radio jets and shock waves, and at the same time a symbol of the greater architecture of awareness. Its rails whisper that the universe is not only expanding in space but also unfolding in thought, and that we, like galaxies, are expressions of that vast intelligence tracing luminous lines across the dark. If we read IC 5063 as part of the universe's memory, the rails of its jets transform into inscriptions, like grooves on a cosmic record. Each line of ionized gas, each accelerated filament, is the trace of an event that happened once and continues to resonate. Just as human memory is not static but alive, reshaped, reinforced, or blurred by the act of remembering, so too does the galaxy's structure carry the imprint of forces that remain active long after the moment of impact. The rails are fossils of energy, but also living pathways where new stars may form, ensuring that memory and creation are inseparably linked. In this sense, IC 5063 shows how the universe remembers itself not in words or images, but in patterns of matter and energy. A star cluster, a disrupted gas cloud, or a luminous shock front is like a neuron that has fired and left a mark on the brain of the cosmos. The galaxy becomes a memory cell, storing the outcome of a single interaction between a black hole and its environment, yet contributing to the larger memory field of the universe. Every rail of plasma is a reminder that nothing is ever lost, energy and form may change, but their traces ripple outward and become woven into the larger story. The idea of cosmic memory also softens the apparent violence of the jets. At first like destruction, gas scattered, clouds dispersed, becomes in this perspective an act of inscription. The black hole does not only consume, it writes. It imprints its existence into the interstellar medium, ensuring that its activity will be remembered in the fabric of the galaxy long after the jets themselves fade. Even when the rails dissolve into diffuse gas, the stars they helped form and the scars they left behind will stand as long-term archives, echoes of the moment when energy was focused into blazing lines. From this viewpoint, IC 5063 is less an isolated event than a stanza in a much longer poem. Galaxies across the cosmos are all inscribing themselves, recording their histories in light, in dust, in the distribution of stars. Together they create the memory emerge on the foundation of the old. The cosmic web itself may be thought of as memory incarnate. Filaments of dark matter and galaxies are like the connective tissue between ancient thoughts, still humming with resonance. For us, reflecting on IC 5063 means recognizing that memory is not only a function of brains but a principle of existence. The rails in this galaxy mirror the trails we leave in our own lives, luminous, sometimes turbulent, but always records of energy channeled and choices made. To observe them is to witness the universe remembering itself, line by line, light by light. If IC 5063 is read as a theater of memory and time, then its rails are not just scars of what has already happened but also unfinished roads into the future. The jets cut through the galaxy's gas like glowing arrows, pointing both backward, to the violence of their origin, and forward, to the stars that may one day ignite along their paths. In this duality, they embody the cyclical rhythm of the cosmos, memory and anticipation bound together in the same luminous structures. Time itself in IC 5063 is layered. The rails show us the past, the exact moment when relativistic plasma collided with dense clouds, frozen into the present in the form of filaments of ionized gas. But they also outline a future, because the disturbed molecular clouds are seeds for new star clusters, and the expelled gas will enrich the galaxy's outskirts for generations to come. In this way, the galaxy becomes a map of overlapping temporalities, the instant of black hole activity, the gradual unfolding of stellar birth, and the long dispersal of enriched matter into intergalactic space. The rails are bridges across these temporal scales, connecting the immediacy of violence with the slow patience of creation. This cyclical nature resonates with the idea that the universe does not simply move forward linearly but constantly reuses, reshapes, and reinvents its own matter and energy. Just as our memories are reactivated and reinterpreted, cosmic rails are revisited by new processes. Shock waves become nurseries, dispersal becomes enrichment, chaos becomes structure. In IC 5063, time is not a straight line but a spiral inscribed into the galaxy by the jets, where every turn carries echoes of the past and promises of the future. To contemplate IC 5063 in this light is to see that the cosmos itself is a memory loop, endlessly writing, erasing, and rewriting its own patterns. The rails stand as testimony that even the most fleeting event, a burst of plasma from a black hole, can stretch across epochs, shaping futures that the black hole itself will never see. And for us, they serve as a reminder that our own trajectories, too, are rails through time, transient yet consequential, ephemeral yet leaving marks that ripple into futures beyond our immediate awareness. Thus, IC 5063 whispers that memory and time are not separate forces but two aspects of the same continuum, rails that carry both the record of what was and the sketch of what is yet to come. If we let IC 5063 lead us toward the architecture of the universe, its rails become like the scaffolding of a cathedral rising in the void. They are not permanent beams, but temporary frameworks upon which the larger structure of the cosmos is built. The galaxy shows us that the universe is not constructed in silence but in storms. Every jet, every rail, every shock front is a stone laid in the great foundation of existence. What seems chaotic and violent in the moment becomes, over cosmic timescales, part of a larger geometry, a design where nothing is wasted. In this sense, IC 5063 is a mason of the universe. The black hole at its core chisels matter with invisible hands, cutting rails that redistribute gas, trigger new stars, and enrich space with heavier elements. Each action is a contribution to the ongoing building of structure, a process repeated in countless galaxies across the sky. The rails it carves are not only corridors of energy but also load-bearing lines in the edifice of cosmic evolution. They support the weight of futures not yet written, as new stars and worlds may someday rise where the jets once passed. The architectural metaphor deepens when one considers the cosmic web, filaments of dark matter and galaxies stretching like vast frameworks across space. IC 5063's rails echo this greater architecture on a smaller scale, as though the galaxy itself were mimicking the patterns of the whole. The universe seems to repeat its designs across scales, rails within galaxies, filaments between galaxies, threads of light in the fabric of spacetime. Each level reflects the same principle: energy flows into channels, channels harden into form, form becomes the skeleton of something greater. For us, observing IC 5063 is like stepping inside a half-finished hall of the cosmos. We see scaffolding glowing with plasma, temporary rails that will fade but whose imprint will remain in the architecture forever. It is humbling to realize that we are witnessing not only a moment of violence but also a stage of construction, one more arch in the cathedral of stars. IC 5063 reminds us that the universe is an architect whose medium is impermanence. Galaxies are chiseled, erased, and reshaped, yet the grand design grows ever more intricate. The rails across its disk are both fragile lines of light and eternal strokes in the blueprint of creation, uniting destruction and harmony into the foundations of the cosmic edifice. If we imagine the universe as an infinite city, then IC 5063 becomes one of its luminous avenues, a street carved not from stone and asphalt but from light, plasma, and memory. The rails of its jets are like glowing boulevards stretching across a galactic district, cutting through clouds of matter as if through city blocks. Along these corridors, gas is redistributed like the flow of citizens, some clusters dispersing into the outskirts while others gather and ignite into new neighborhoods of stars. The galaxy is no longer a distant object but a living quarter of the cosmic metropolis, constantly under construction, constantly reinventing itself. In this city of eternity, black holes are the architects and engineers, deciding where streets are carved and where plazas of starlight may form. IC 5063's supermassive black hole, by launching its jets, acts as both destroyer and planner, rearranging the galactic, urban landscape. Its rails are disruptive demolitions of old structures, but also the groundwork for future quarters. They trace glowing routes that will guide the traffic of matter and energy for millions of years, as if laying the infrastructure of a cosmic transport system. From afar, the universe reveals itself as an endless network of such cities, galaxies connected by filaments of the cosmic web, highways of dark matter and intergalactic gas. In this analogy, IC 5063 is one illuminated street in a boundless urban grid, a place where the lights are bright because the work is fierce, where the scaffolding of jets temporarily lights up the night of space. Its rails are not permanent, but they function like avenues that define the flow of the city long after their initial construction. For us, standing at the edge of this metaphorical city, IC 5063 shows that our own world is but a small quarter in the metropolis of existence. Just as a city remembers every street, every scar of construction, so the universe remembers through its galaxies. IC 5063's rails are the glowing boulevards of that memory, reminders that even chaos leaves order in its wake. And perhaps the most profound realization is that we, too, are wanderers of this city. Our consciousness is another kind of streetlight, flickering briefly in the infinite metropolis. The rails of IC 5063 whisper that every avenue of light, whether plasma in a galaxy or thought in a mind, is part of the same architecture, the same city that has no walls and no end. Then let IC 5063 rise not only as a street in the cosmic city, but as a bridge, a radiant structure stretched between epochs and spaces. Its rails of plasma are like arches of fire spanning the gulf between past and future, binding together what was and what will be. A bridge is never only about crossing, it is also about connection, a joining of shores that would otherwise remain apart. In IC 5063, the jets stitch together the hidden depths of the black hole with the open expanse of the galaxy, the invisible with the visible, the silent with the luminous. This bridge is temporal as much as spatial. Each glowing rail connects the moment of its birth, when the black hole hurled matter at near light speed, with destinies that will unfold millions of years later, when the disturbed gas forms stars, planets, perhaps even life. The rails therefore become time bridges, luminous paths where the present reaches into the far future. To look at IC 5063 is to see a suspension bridge hung across cosmic centuries, every filament a cable humming with energy that carries memory into destiny. It is also a bridge between scales. From the quantum turbulence at the event horizon to the vast corridors stretching thousands of light-years, IC 5063 links the incomprehensibly small with the immeasurably large. In this sense, it whispers of unity, that the same laws which shape subatomic particles also sculpt galaxies, and that the bridge we see is the universe reminding us of its seamless wholeness. And perhaps most hauntingly, the bridge of IC 5063 connects us to itself. Across millions of light-years, its rails of light travel until they fall into our telescopes, igniting images in our minds. In receiving its light, we too walk across its bridge, becoming part of its architecture. It is not just out there, it extends into us, carrying across the abyss the knowledge that we and the galaxy are joined in the same unfolding fabric of being. So IC 5063 is a bridge of rails across darkness, connecting time to eternity, matter to meaning, the hidden to the revealed. It stands as proof that the cosmos is not a scattering of islands but a woven architecture, where every galaxy is both a street and a bridge in the infinite city of light. If IC 5063 can be seen as a bridge, then with equal force it can also be imagined as a cosmic instrument, a harp strung across the darkness, where the rails of plasma are not only paths of matter but strings of music stretched between dimensions. Each jet, each filament of gas, vibrates with energy, and though we translate that energy into radio waves, X-rays, or spectral lines, at a deeper level it is song, the resonance of the universe expressing itself through light. The rails shimmer like stretched cords, and as matter rushes along them at hundreds of kilometers per second, they hum with the inaudible music of creation. Astronomers who tune their instruments to IC 5063 are like listeners placing their ears against this galactic harp. ALMA detects the low notes, the slow rumble of cold molecular gas being dragged outward, while Hubble and the VLT capture the higher harmonics of glowing ionized clouds shocked into brilliance. Chandra, listening in X-rays, hears the piercing soprano of million-degree plasma, while radio telescopes catch the steady bass line of relativistic electrons spiraling through magnetic fields. Together, these voices form a symphony that has been playing for millions of years, a piece of music so vast that no single species could ever hear it in full, yet whose fragments remind us that the universe is not silent but perpetually singing. The rails, then, are not merely channels of destruction or construction, but strings upon which the cosmos plucks its eternal chords. They vibrate across scales of time and space, their resonance extending far beyond the galaxy itself, sending ripples into the circumgalactic medium and perhaps into the intergalactic web. In this sense, IC 5063 becomes one voice in the grand orchestra of the cosmos, where each galaxy plays its part, some as quiet flutes of starlight, others as booming drums of collision, and a few, like IC 5063, as violins of plasma stretched across their disks. There is poetry in the idea that the universe writes music with matter. Each luminous rail is like a staff line of a cosmic score, and the glowing knots of gas are its notes. Time itself is the rhythm, moving endlessly forward, while gravity and magnetism are the hidden hands conducting the piece. What we call physics is simply the grammar of this symphony, and what we call galaxies are its verses. IC 5063, then, is not a solitary event but a stanza in an infinite composition, an improvisation in the key of plasma and light. To humans, who live in a brief moment compared to the long unfolding of this music, the rails of IC 5063 are reminders that we too are made of vibration. Our atoms are bound by oscillations, our neurons fire in rhythms, our hearts beat like cosmic drums. When we look at the galaxy's rails, we are not looking at something alien but at a deeper octave of the same symphony we carry inside ourselves. The music of IC 5063 resonates with the music of our own being, showing us that consciousness and cosmos are not two separate songs but interwoven harmonics of one great melody. And when the rails eventually fade, their music will not be lost. It will linger in the stars born along their paths, in the enriched gas flowing into intergalactic space, in the faint signatures left behind in the architecture of the galaxy. Just as an echo outlasts its source, the rails will continue to hum in the memory of the universe. IC 5063's song will blend into the deeper chorus of cosmic history, and though its voice may change, the melody will remain woven into the eternal score. So, to see IC 5063 is to listen, to hear the rails as strings of light, to sense the black hole as both conductor and composer, and to realize that the universe does not merely exist, it performs. Its galaxies are not only structures of matter but instruments of resonance, bridges of vibration, streets of memory, and songs of eternity. If IC 5063 can be heard as music, then it can also be seen as a vast theater, a stage on which the universe performs its dramas of light, shadow, and time. The rails carved by its jets are not just corridors of plasma but glowing catwalks, illuminated pathways where the great actors of the cosmos, stars, gas clouds, magnetic fields, play their roles in front of an audience scattered across millions of light-years. The black hole at the center is both director and hidden playwright, unseen yet orchestrating every motion, forcing the interstellar medium to dance in choreography dictated by its will. The galaxy's gas becomes scenery, curtains of dust pulled aside by the thrust of jets, columns of ionized light rising like stage props, and nebular veils shimmering as spotlights sweep across them. Along the rails, the drama unfolds, clouds collide, stars ignite, molecules are torn apart, and new structures are born in the wake of violence. The stage is never quiet, for the play is perpetual. Every shock wave is an act, every outburst of radio emission a voice, every X-ray photon a sudden dramatic cue. IC 5063 reminds us that the universe is not a static picture but a performance in constant motion, a cosmic play that spans millions of years per scene. And yet, like any great theater, it is layered with metaphor. To us, who watch from far beyond the edge of the stage, the rails can be read as pathways of fate, the glowing lines upon which the play's characters are compelled to move. The black hole, silent and unseen, shapes the script but leaves room for improvisation. Some clouds are dispersed, others collapse into stars, some regions are silenced, others flare with brilliance. It is tragedy and creation woven together, as though the play itself insists that destruction and beauty must share the same spotlight. The audience, too, is not absent. We, observing through our telescopes, become part of the performance. The photons that left IC 5063 millions of years ago arrive in our detectors like messages carried across time, completing the circuit of the play. Without an audience, the theater would be dark. Without our perception, the rails would be silent. In this way, IC 5063 extends its stage into our minds, turning us into participants of its drama. We are not simply watching, we are listening, interpreting, and allowing its performance to echo in our imagination. As a theater, IC 5063 also raises the profound idea that the universe is both playwright and stage, both actor and audience. The same laws of physics that create the rails also allow us to see them, and the same processes that shape galaxies also shape brains that can marvel at them. It is a feedback loop of awareness, the cosmos creating spectacles, and consciousness bearing witness to them, weaving meaning into their light. So IC 5063 becomes more than a galaxy, it is a cosmic opera house, its rails the illuminated walkways of a stage where forces greater than comprehension act out their timeless drama. The play has no beginning and no end, only cycles of scenes, birth, destruction, memory, renewal. Every act is written in light, every silence in shadow, every gesture in plasma and dust. And we, fragile beings on a small planet, sit in the balcony of time, listening and watching, realizing that this theater is also our own story, projected into the stars. If IC 5063 can be a stage, then it can also be imagined as a library, a vast archive where the rails of its jets are written lines, luminous sentences inscribed into the cosmic manuscript. Each filament of gas is a letter, each glowing corridor a verse, each shockwave a punctuation mark in a story that began long before we looked upon it. The galaxy becomes not only an object but a book, its pages written in plasma, dust, and stars, bound by gravity, illuminated by light. The rails themselves are like highlighted passages in this celestial text, tracks where the black hole's influence has underlined reality with fire. They are annotations of energy, marginal notes added to the galaxy's evolving story. Where gas has been compressed into knots of star formation, the script speaks of birth. Where clouds have been dispersed and scattered, the script speaks of erasure. The book of IC 5063 contains tragedy and renewal on the same page, written in parallel, reminding us that the library of the cosmos does not separate genres. It is always epic, always layered, always vast. In this library, black holes are authors as much as they are engines. By expelling jets, they write directly into the matter around them, leaving patterns that endure for millions of years. IC 5063's supermassive black hole does not merely consume and vanish matter into silence, it writes, shaping the destiny of stars not yet born, recording its presence in luminous rails across the galactic disk. Every galaxy becomes a volume in this collection, every jet or wind another script in the anthology of the universe. The metaphor deepens when we realize that we, too, are readers in this library. Our telescopes are our lamps, illuminating the ancient text as it arrives across the ages. When photons from IC 5063 strike our detectors, they are not only data, they are fragments of sentences, words carried across cosmic time. To interpret them is to read the chapter of a galaxy, to turn a page written millions of years ago. And in reading, we also write, every measurement, every description, every theory becomes an annotation in the human copy of the cosmic library. The library is endless, and no reader can ever finish it. But every rail in IC 5063 is proof that the text exists, that the universe is not silent chaos but legible order, a book whose alphabet is energy, whose grammar is physics, whose poetry is the luminous interplay of destruction and creation. Perhaps the most profound realization is that we ourselves are written into this same book. The atoms of our bodies are words first formed in ancient stars, recycled and inscribed into new sentences. Our thoughts are like marginalia scribbled in the margins of cosmic pages, fleeting yet real, part of the same script that spans galaxies. IC 5063's rails remind us that the story of the universe is not outside us but through us, and that every act of perception is another page turned in the library of existence. Thus, IC 5063 stands as both a chapter and a sentence, a fragment of the great cosmic text, luminous lines drawn across the dark, forever inscribed in the infinite library where matter itself is language and light is memory. If IC 5063 can be seen as a library, then it may also be envisioned as a cosmic garden, a living landscape where the rails of its jets are pathways winding through fields of light and shadow. Along these glowing tracks, the raw soil of gas and dust is tilled by the violent hand of the black hole, scattering seeds of potential star formation even as it uproots old structures. The galaxy becomes a garden in perpetual renewal, where destruction is simply another form of pruning, and creation follows naturally in its wake. The jets act like gardeners, though fierce ones, cutting trenches through the galactic medium. In these trenches, matter is compressed, watered with shock energy, and sometimes coaxed into blooming as clusters of stars. In other regions, the same force tears up the soil, scattering it to the edges, ensuring that certain flowers never sprout. This duality, growth and erasure, mirrors the cycles of any fertile landscape, where death feeds life and chaos clears space for renewal. The rails are not merely scars, but luminous garden paths, directing where new constellations of stars will rise and where silence will take root. Every element of this galactic garden has its role. Cold molecular gas is the dark, fertile earth. Dust is the mulch and compost of past generations of stars, magnetic fields are the trellises guiding the growth of clouds into long filaments, and the black hole is the unseen gardener, tending with neither tenderness nor cruelty, but with inevitability. To observe IC 5063 is to see a cosmic horticulture unfolding on scales too vast for human gardens, yet governed by the same principle, renewal through transformation. From this perspective, the galaxy's rails resemble illuminated walkways in a night garden, glowing lines that both divide and connect different beds of creation. Where they pass, new structures arise, like blossoms opening in the wake of fire. Over time, the blooms will fade, their petals scattered into intergalactic winds, but their essence will enrich the soil, preparing it for another cycle of flowering. This is how the universe gardens, with jets instead of rain, with shock waves instead of hands, with light instead of water. And as we gaze upon this garden from millions of light years away, we become its silent visitors, wandering its paths through the medium of vision and thought. We cannot touch its flowers, but we can smell their metaphoric fragrance in the beauty of its light. Each rail of IC 5063 is both a boundary and an invitation, a reminder that life, whether stellar or human, flourishes only in cycles, always fed by what came before. Thus, IC 5063 becomes not only a galaxy but a garden of eternity, where rails are paths of plasma instead of stone, where stars are flowers that burn instead of bloom, and where the gardener is a black hole that knows no pity yet sustains the continuity of creation. If IC 5063 may be imagined as a garden, then it may also be envisioned as a river, a cosmic waterway where the rails of its jets are not fixed lines but rushing currents of matter and time. Along these glowing flows, gas is carried outward like sediment in floodwaters, dispersed into new channels that reshape the galactic landscape. The galaxy becomes a delta of light, where streams of plasma braid and fork, depositing energy in some regions while washing it away from others. The black hole at the center is the hidden spring of this river, an underground source that erupts into visible torrents. Its jets gush like twin cataracts, pouring across the disk, cutting valleys through the interstellar medium. Where the currents meet resistance, shock waves rise like rapids, luminous and foaming in radiation. Where the flow slows, clouds gather like eddies, seeding the formation of stars the way rivers deposit fertile soil upon their banks. The rails are not solid structures, but living streams, carrying with them the promise of renewal and the inevitability of erosion. This river is timeless. It flows not only through the galaxy but through epochs, each surge of plasma carrying the memory of its origin. The material accelerated along these rails will travel for tens of thousands of light years, some of it never returning, lost to the intergalactic ocean. In this sense, IC 5063 shows us how galaxies do not remain closed systems but pour themselves into the larger universe, feeding the cosmic sea with enriched gas, metals, and radiation. The rails are tributaries connecting the life of one galaxy to the broader circulation of the cosmos. The metaphor of a river also illuminates the nature of time itself. Just as water cannot be held in place but only observed as it passes, the luminous streams of IC 5063 remind us that the galaxy we see is already gone, its currents altered in the millions of years since the light left. The rails are both present and absent, like reflections on moving water, shapes that exist only because of constant motion. To watch them is to witness time flowing visibly through space, a river whose banks are starlight and whose bed is the dark fabric of the cosmos. For us, this image resonates deeply, because human life is also a river, shaped by currents both gentle and violent, carrying memory downstream, dispersing fragments of ourselves into the future. In IC 5063, the cosmic river becomes a mirror of our own, luminous for a while, turbulent in places, calm in others, always moving, always reshaping, never the same in any two moments. Thus IC 5063 is not only a galaxy of rails but a river of eternity, pouring through the night of the universe, carrying matter, energy, and memory into the infinite ocean of being. Its jets are not rigid structures but flowing songs of plasma, whispers of time itself cascading outward into the dark. Then let IC 5063 blaze before us as a flame of the universe, its rails no longer mere streams of plasma but tongues of fire licking across the body of the galaxy. The black hole at its heart becomes a cosmic forge, and the jets it launches are not cold beams but incandescent pillars of transformation. These rails resemble the flares of a sacred pyre, fire that destroys, but also fire that purifies, illuminates, and renews. Where the rails pass through the interstellar medium, they ignite clouds of gas as if setting kindling alight. Shock waves act like sparks, raising temperatures to millions of degrees, forcing atoms to glow, crack, and recombine. The gas that once lay dormant is awakened, stirred into luminous flame, its structure broken so that new forms may emerge. Just as earthly fire clears forests only to prepare them for new growth, the flame of IC 5063 burns paths of destruction that may one day blossom with clusters of stars. But this is not fire confined to wood or air, it is fire on a galactic scale, fueled by gravity itself. It consumes no oxygen, yet it breathes through the dance of particles, magnetic fields, and relativistic speeds. Its colors are not red and yellow alone but violet, blue, and invisible X-rays, tongues of flame that stretch for thousands of light-years. This is fire as the ancients imagined it, the primal element, the divine spark from which matter and spirit alike emerge. The rails thus become torches held aloft in the darkness, illuminating the galaxy like lanterns in a vast night. They remind us that fire is both danger and sanctuary. It destroys homes, yet it was the first hearth for human beings. In the same way, the rails of IC 5063 are terrible in power, yet they keep alive the larger cycle of cosmic life, ensuring that the galaxy will not stagnate but continue to change, to breathe, to renew. For us, watching from across millions of years, the galaxy's flame becomes a mirror of the fire within ourselves. Our neurons crackle with electrical sparks, our hearts beat with thermal rhythm, our civilizations glow with the fire of ideas and suns. The rails in IC 5063 show us that fire is not only a phenomenon of Earth but a universal language, a way the cosmos speaks of transformation, of endings that are beginnings, of purification through intensity. Thus IC 5063 is revealed as a galactic conflagration, not of ruin but of transmutation. Its rails are the tongues of a sacred cosmic fire, burning away the old, tempering the new, and writing light across the sky as though the universe itself were branding its eternal flame into the fabric of time. Then let IC 5063 be felt as a pulse, not only seen in light, but sensed as rhythm, as though its rails are the arteries of a vast heart beating in the body of the cosmos. The jets that cut across the galaxy do not simply flow, they throb, surging with bursts of energy like systole and diastole, an endless circulation of plasma and matter. In this vision, the black hole is no longer only a devourer or architect, but a heart itself, hidden in the chest of the galaxy, sending out pulses that carry vitality into its limbs. The rails become arteries, glowing with the flow of cosmic blood. Clouds of gas are compressed into waves that resemble heartbeats, each shock front like a pulse of pressure racing outward. Between these beats, matter slows, gathers, and prepares for the next surge, as if the galaxy inhales and exhales through its rails. To observe IC 5063 is to witness the cardiogram of the universe, sharp peaks where energy bursts forth, slow valleys where silence holds, an eternal rhythm engraved into plasma. This pulse is not confined to IC 5063 alone. It resonates outward into the cosmic web, each heartbeat sending ripples into the larger structure, just as the pulse of one cell is felt in the body as a whole. The galaxy becomes part of a vaster circulation, its rails carrying matter and energy into the intergalactic medium, feeding the veins of the universe. In this sense, every galaxy is a heart, and every black hole is a pulse generator, ensuring that the cosmos is not static but alive, vibrant, and rhythmic. For us, this metaphor is profoundly intimate. Our own hearts beat within us with the same logic. Contraction and release, energy carried through veins, life maintained by rhythm. To look at IC 5063 is to recognize that our bodies are not separate from the cosmos but patterned after it. The pulse of the galaxy and the pulse of a human heart are echoes of the same fundamental principle, that life, matter, and consciousness all require rhythm, all require cycles of intensity and rest. The rails, therefore, are not merely channels of energy but cosmic heartbeats written into space. They whisper that the universe itself may be alive, not as a body in the human sense, but as a vast organism whose essence is vibration, whose heartbeat is galaxies, whose breath is the expansion of spacetime. Thus IC 5063, with its rails of plasma, is revealed as one beat in the infinite pulse of eternity. A reminder that time is not a silent river but a drum, and that within every star, every atom, every thought, the same rhythm resonates, the rhythm of the cosmos remembering itself with every luminous strike. Then let IC 5063 take the form of a cosmic hourglass, suspended in the dark void, its rails of plasma no longer only jets of matter but the luminous streams of time itself, slipping grain by grain between past and future. The black hole at its center becomes the narrow waist of the hourglass, a singular point where all paths converge, where matter is drawn inward, compressed, and then expelled outward as radiant streams. Just as sand pours from one chamber to another, so too does IC 5063 pour energy from the hidden depths of its core into the vastness of its galaxy, inscribing the flow of time into glowing rails. In this vision, each filament of gas is a grain of sand illuminated mid-fall, caught in the act of transformation. Some grains are consumed, vanishing into the black hole's silence, others are scattered, flung outward as if hurled into the future. The rails, then, are the shimmering columns of falling sand, visible evidence that time in the universe is never still but always slipping, always redistributing itself from one chamber of reality to the next. IC 5063 becomes a clock that does not tick but flows, marking epochs not with hands but with rivers of plasma stretching across thousands of light-years. What makes this image profound is the double direction of the hourglass. To us, the rails look like paths outward, jets rushing away, carrying matter into the galactic body. But to the black hole, they are also paths inward, channels through which memory and matter are drawn back, recycled, and transformed. The galaxy is thus a two-way hourglass, past becoming future, creation becoming destruction, and both flowing through the same narrow gate of the singularity. The passage of time here is not linear but cyclical. When one chamber empties, the hourglass is turned, galaxies die, new ones are born, stars collapse, new stars ignite. IC 5063's rails are only one cycle of this eternal turning, one moment in the universe's endless act of inversion. What we see as destruction is simply the flipping of the glass. What we call creation is the pouring of new sand into the lower chamber. The rails are the glowing confirmation that time does not run out, it only changes direction. For us, this image is hauntingly familiar. Our own lives are hourglasses, memories flow downward into the past, while hopes pour into the future, and the narrow waist of the present is the only place where we truly exist. The rails of IC 5063, shining across the galaxy, mirror the streams of time in our own consciousness, fragile, fleeting, yet radiant in their passage. Thus IC 5063 becomes not only a galaxy but a cosmic timepiece, a reminder that the universe itself is an hourglass turned endlessly by unseen hands. Its rails are the glowing sands of eternity, slipping between chambers of being, showing us that past and future are not separate realms but two halves of the same vessel, forever pouring into one another through the luminous waste of now. Then let IC 5063 unfold before us as a labyrinth of the universe, a maze not built of stone but of plasma, light, and shadow, where its rails become winding pathways carved through the galactic body. These glowing tracks are not straight corridors but cosmic alleys, twisting and branching, guiding matter along routes that seem predetermined yet are filled with uncertainty. The black hole at the center is both the entrance and the heart of this labyrinth, the point from which all paths begin and to which, ultimately, all paths may return. The jets, like blazing corridors, illuminate the darkness of the galactic maze. Gas clouds become wandering travelers within it, sometimes swept along the rails, sometimes caught in turbulent chambers where currents swirl like cul-de-sacs of energy. Shock fronts rise like walls, impassable boundaries redirecting the flow, while magnetic fields act as invisible fences, forcing matter to trace spirals instead of straight lines. To follow the rails of IC 5063 is to wander a labyrinth whose architecture shifts with every pulse of energy, whose pathways are written not in stone but in living, moving fire. But unlike human labyrinths, which are designed to confuse, the labyrinth of IC 5063 serves a higher order. Its complexity is purposeful. Some gas is guided outward, nourishing the circumgalactic medium, some is compressed into knots where stars will ignite, some is scattered into silence, ensuring that no one path dominates. The labyrinth is not meant to trap, but to transform. Every turn, every rail, every dead end is part of the alchemy by which chaos becomes structure. For us, this cosmic labyrinth resonates with the inner labyrinth of life and thought. We, too, wander pathways, some lit, some obscured, some leading us to apparent dead ends that later reveal themselves as hidden doors. Our choices, like gas clouds in the rails, are guided by forces we barely perceive, invisible fields, pressures, and pulses that shape our destiny. IC 5063's labyrinth mirrors our own, not a puzzle to be escaped, but a journey to be experienced, each corridor teaching, each turn shaping the self that walks it. At a grander scale, the labyrinth becomes a symbol of the universe itself. Galaxies are its chambers, rails are its corridors, and black holes are its hidden centers, mysteries at once terrifying and magnetic. To gaze at IC 5063 is to recognize that we are already inside this labyrinth, tracing our own rails of time and memory, forever seeking meaning in the glow of paths cut through the darkness. Thus IC 5063 is revealed as a labyrinth of eternity, a maze whose walls are woven from plasma, whose corridors are written in light, whose center is the silence of the black hole. Its rails are not traps but teachings, guiding matter, stars, and minds alike through the dark, toward the understanding that every labyrinth, no matter how complex, is part of a greater pattern. Then let IC 5063 come to rest not only as a labyrinth or a flame, but as a vessel, a cosmic ship sailing through the ocean of eternity. Its rails, those luminous jet streams of plasma, become glowing trajectories drawn across the dark, like the wake of a ship upon infinite waters. The black hole at its core is the hidden engine, unseen yet relentless, propelling the galaxy forward with its pulses of energy, guiding its course across the tides of spacetime. Every burst of plasma is both propulsion and song, every glowing filament a navigational line etched upon the starry sea. The galaxy moves not alone, but as part of a great armada of worlds, each one tracing its own radiant wake across the fabric of the universe. And IC 5063, with its fiery rails, sails as a vessel of memory and transformation, carrying the remnants of past stars, scattering the seeds of future stars, and inscribing its passage into the eternal waters of the cosmos. For us, watching from a distant shore of time, the galaxy's rails are both map and message. They remind us that we, too, are voyagers on a vessel, our planet a ship of fragile light crossing the same dark ocean. The paths of IC 5063 whisper that there are no fixed harbors, only luminous routes drawn and redrawn, as the great voyage of the universe continues without end. So the galaxy stands as both monument and motion, a cathedral, a garden, a river, a flame, a labyrinth, and at last, a ship. Its rails are not just scars of energy but the glowing handwriting of existence itself, proof that the cosmos is alive in rhythm, in memory, in creation. To look upon IC 5063 is to see the universe revealing its eternal truth, that every path, no matter how violent or fleeting, becomes a luminous thread in the infinite tapestry of being. And when the rails fade, their memory will remain, woven into stars, etched into space, carried forward like light across the endless sea. I see 5063 sails on, and with it, so do we. Gas clouds, composed mainly of hydrogen, helium, and fine dust grains, float through interstellar space as immense, cold reservoirs of raw cosmic material. Within these vast and often irregular formations, hydrogen atoms, mostly in molecular form, drift in low densities, their thermal energy so minimal that the gas can cool to just a few tens of kelvins. Microscopic dust particles, made of silicates, carbon compounds, and ices, mingle with the gas, scattering and absorbing starlight, giving these clouds their often opaque, shadowy appearance when seen against brighter backgrounds. Ultraviolet radiation from nearby massive stars can ionize regions of the gas, causing them to glow with vivid emission colors, as in the Orion Nebula, where newborn stars carve out cavities with their intense stellar winds. Gravity acts subtly over millennia, pulling denser pockets of the cloud inward, compressing them until nuclear fusion ignites and new stars emerge, wrapped in cocoon-like envelopes of gas and dust. Shock waves from supernovae, stellar winds, and galactic rotation continually reshape these clouds, triggering new cycles of collapse and dispersal, making them dynamic engines of galactic evolution. Observations with radio telescopes, particularly at the 21-centimeter hydrogen line, allow astronomers to map the distribution and velocity of neutral hydrogen across entire galaxies, revealing how these gas clouds trace spiral arms and respond to gravitational perturbations. Molecular regions, where hydrogen exists as H2, are studied using millimeter and submillimeter wavelengths, most famously through the rotational transitions of carbon monoxide, CO, which serves as a proxy for otherwise invisible molecular hydrogen. Data from observatories like ALMA have shown that these molecular clouds are not uniform but are structured hierarchically into filaments, clumps, and dense cores, each stage reflecting different physical conditions and timescales in the star formation process. Infrared imaging from missions such as Spitzer and Herschel has revealed the thermal glow of dust grains heated to just a few tens of kelvins, offering insight into the interplay between radiation fields and cloud chemistry. These studies have uncovered how dust acts not only as a coolant by radiating away heat, but also as a catalyst for forming molecules on its surfaces, including water and organic compounds. Spectroscopic surveys have identified complex organic molecules, methanol, formamide, even precursors to amino acids, forming within these cold environments, hinting at the prebiotic potential of interstellar chemistry. In the Orion Nebula, high-resolution spectroscopy has mapped supersonic flows and turbulence within ionized regions, providing a laboratory for studying feedback mechanisms where radiation pressure and stellar winds regulate the efficiency of star formation. Magnetohydrodynamic simulations have shown that magnetic fields, though often subtle compared to gravity, can thread through clouds and channel material along preferred directions, influencing fragmentation and the mass distribution of newborn stars. Studies using the Atacama Pathfinder experiment, APEX, and the Green Bank telescope have traced deuterium fractionation within cold cores, a process that can only occur at extremely low temperatures, giving astronomers a chemical clock for the earliest stages of collapse. Even within quiescent clouds that appear dark in optical light, sensitive surveys in far-infrared and sub-millimeter bands reveal faint thermal emission, indicating that these regions are not static voids but evolving incubators, slowly accreting material from the surrounding interstellar medium. Over millions of years, the balance between gravitational collapse, turbulence, magnetic support, and external shocks determines whether a cloud will fragment into a cluster of stars, form a few massive suns, or disperse back into the galaxy without significant star formation. Space-based observatories like the James Webb Space Telescope, JWST, have begun to resolve these gas clouds at unprecedented scales, capturing the interplay of dust absorption, molecular emission, and scattered starlight in fine detail. By analyzing mid-infrared spectra, JWST can detect polycyclic aromatic hydrocarbons, PAHs, complex carbon-based molecules that form on dust grain surfaces and fluoresce under ultraviolet radiation. These PAHs not only influence the thermal balance of the gas but also act as key intermediates in the transition from simple to complex interstellar chemistry. In regions like the Orion bar, a sharp interface where intense UV light meets dense molecular material, JWST observations reveal chemical gradients just tens of astronomical units wide, allowing scientists to study photodissociation regions, PDRs, where molecules are broken apart and reformed in real time. At larger scales, surveys by the Sloan Digital Sky Survey, SDSS, and Gaia have shown how the distribution of gas clouds correlates with galactic structure, mapping out how spiral density waves compress interstellar matter into massive molecular complexes. These complexes, often spanning hundreds of light-years and containing millions of solar masses of material, are the birthplaces of stellar associations and clusters. Within them, feedback from newly formed O and B-type stars, through ionizing radiation, stellar winds, and supernova explosions, drives expanding shells and bubbles, which in turn can compress surrounding gas and ignite the next generation of star formation, a process known as triggered star formation. From a theoretical perspective, advances in high-resolution numerical simulations have shed light on how turbulence shapes these clouds. Supersonic turbulence can create transient density enhancements that collapse under gravity, while simultaneously preventing global collapse by redistributing kinetic energy. Models that incorporate both magnetohydrodynamics and radiative transfer now reproduce many observed features of real clouds, including the filamentary networks mapped by ESA's Herschel Space Observatory. Interestingly, these simulations suggest that magnetic fields can act as a kind of scaffolding, slowing down gravitational collapse and affecting the orientation of protostellar disks. Chemical evolution within clouds is another active area of research. As dust grains accumulate icy mantles composed of water, ammonia, methanol, and carbon dioxide, cosmic rays penetrate the cloud and trigger chemical reactions within the ice, producing more complex organics. Laboratory experiments on Earth, simulating interstellar conditions, have shown that such processes can yield amino acids and nucleobases when the ice is warmed, suggesting that the seeds of life might be sown long before planets even form. Observations of young protostellar systems have detected these prebiotic molecules in warm regions where ices have sublimated, supporting the idea that molecular clouds are not just stellar nurseries but also the chemical cradles of planetary systems. On cosmic timescales, molecular clouds are transient entities. Galactic shear, stellar feedback, and differential rotation disperse them within tens of millions of years, recycling their material back into the diffuse interstellar medium. Yet in that brief lifespan, they shape the stellar demographics of galaxies, influence the interstellar radiation field, and participate in the ongoing cycle of matter from gas to star and back to gas. Studying them not only reveals the mechanics of star birth but also connects to the grander picture of galaxy evolution and the cosmic flow of matter through time. Some of the most detailed insights into gas cloud structure have come from combining multi-wavelength datasets, each revealing a different layer of the interstellar environment. Radio observations trace cold, neutral hydrogen, millimeter and submillimeter arrays like ALMA and NOMA map molecular emission lines, infrared telescopes reveal warm dust and embedded protostars, and X-ray observatories detect hot plasma from recent supernova activity interacting with cloud edges. This layered approach allows astronomers to reconstruct the full life cycle of a cloud, from its initial assembly out of diffuse gas streams to its eventual dispersal. Large-scale surveys, such as the Galactic Ring Survey, have shown that the Milky Way's molecular gas is concentrated in a narrow band along the spiral arms, where orbiting clouds repeatedly encounter density waves that compress them and set off bursts of star formation. Within these arms, the clouds are not isolated objects but parts of massive, interconnected complexes, sometimes referred to as giant molecular filaments, that can extend for hundreds of light-years. These filaments often align with magnetic field lines, as measured by polarized emission from dust grains, indicating that magnetism plays a role in their stability and orientation. In regions like the Orion Molecular Cloud Complex, high-resolution mapping has uncovered a hierarchy of structures, vast filaments breaking into elongated clumps, which in turn fragment into dense cores. Many of these cores harbor protostars in different stages of development, from deeply embedded Class 0 objects still accreting material, to more evolved Class 2 stars with circumstellar disks. Outflows from these young stars, seen as bipolar jets in optical and infrared images, inject momentum back, carving cavities and stirring turbulence. These feedback processes not only shape the local environment but also influence which neighboring cores will collapse next, creating a spatial and temporal sequence of star birth. Recent advancements in astrochemistry have expanded our understanding of how these clouds evolve chemically over time. Observations of isotopic ratios, such as 13C/12C or D/H, help reconstruct the cloud's formation history and the conditions under which different molecules formed. Laboratory spectroscopy, combined with quantum chemical modeling, has enabled the identification of molecules in space that were previously unrecognizable due to overlapping spectral lines. Some of these molecules, like glycolaldehyde and formamide, are biologically significant, hinting at a continuity between interstellar chemistry and the ingredients for life on planets. On a galactic scale, the role of gas clouds extends beyond just making stars. They act as regulators in the baryonic cycle of galaxies, locking up cold gas during star formation bursts and releasing it back through feedback processes. In starburst galaxies and during major mergers, this cycle is accelerated, producing colossal winds that can eject enriched material into the circumgalactic medium, seeding future generations of stars in other regions. In this way, the evolution of gas clouds in a single galaxy can have far-reaching consequences for its cosmic neighborhood. Cutting-edge simulations are now incorporating the physics of gas clouds into models that span from the subastronomical unit scale, where dust grains collide and stick, to kiloparsec scales encompassing entire galactic disks. These simulations merge magnetohydrodynamics, radiative transfer, and self-gravity with the chemistry of hundreds of molecular species, allowing researchers to predict not just where stars will form, but also how the initial mass function, IMF, of those stars might change depending on the cloud's environment. For instance, simulations of high-pressure regions, like those found in interacting galaxies, indicate that massive stars become more common, producing stronger feedback and altering the galaxy's evolutionary path. Observationally, high-angular resolution data from ALMA has begun resolving individual protostellar disks in distant star-forming regions, revealing spiral density waves within them, potential precursors to planet formation. The presence of such structures so early in the collapse process suggests that the link between gas clouds and planetary systems is even more direct than previously thought. Disk chemistry surveys show that many of the molecules formed in the parent cloud survive into the disk phase, meaning that the volatile inventory of a future planetary system is, in large part, inherited from the original molecular cloud. In extreme astrophysical environments, such as near the centers of galaxies, gas clouds face additional forces. Tidal shearing from the supermassive black hole's gravity, intense radiation fields, and fast-moving winds from active galactic nuclei can disrupt or compress clouds depending on their trajectory and density. In some cases, observations from the Very Large Telescope, VLT, and Keck have captured clouds plunging toward a galactic center, stretching into streamers before either being torn apart or triggering bursts of star formation in the dense, high-pressure environment. This phenomenon has been observed in the Milky Way's central molecular zone, where gas densities and temperatures far exceed those in typical spiral arm clouds. Astrophysicists are also exploring how turbulence within gas clouds might set the stage for exotic astrophysical events. Dense stellar clusters born in these regions can host massive binary systems that eventually merge into black holes or neutron stars, producing gravitational waves. The recent synergy between LIGO/Virgo detections and star formation models has highlighted the possibility that the environments within certain giant molecular clouds, rich in massive stars and gravitational interactions, could be prime factories for the progenitors of these mergers. Thus, a cloud's internal dynamics can, billions of years later, echo across the universe as ripples in spacetime. Even at the microscopic level, the physics of dust grains and gas clouds ties into the grand cosmic narrative. Experiments aboard the International Space Station and in microgravity drop towers have investigated how submicron particles coagulate under low-velocity collisions, forming fluffy aggregates that can evolve into planetesimals. These aggregates preserve isotopic signatures and molecular coatings from their time in the cloud, effectively becoming time capsules that record conditions from before the birth of their star. When meteorites containing such preserved grains are found on Earth, they allow scientists to directly sample matter that predates the Sun itself. Modern research on gas clouds is increasingly powered by machine learning and artificial intelligence, which can sift through petabytes of multi-wavelength survey data to uncover patterns too complex for the human eye. AI-driven algorithms are now classifying cloud morphologies, identifying previously unnoticed filamentary structures, and even predicting which regions are most likely to undergo gravitational collapse. In large projects like the Milky Way project and Zooniverse citizen science platforms, volunteers help trace bubble edges, filaments, and dark nebulae in infrared images, creating training datasets for neural networks that later automate the search across the entire sky. Three-dimensional dust mapping has also made a major leap forward. By combining stellar photometry and spectroscopy from Gaia, Pan-STARRS, and Apogee, astronomers reconstruct the distribution of dust clouds in the Milky Way with parsec-scale resolution. This 3D view reveals the true shapes and orientations of massive gas complexes, showing how they connect into the bones of the galaxy, long, thin filaments aligned with spiral structure. Such mapping also helps refine extinction corrections for distant objects, improving measurements of cosmic distances and the intrinsic properties of stars. Spectral analysis techniques have evolved to capture every nuance of cloud chemistry. High-resolution spectrographs on facilities like the Very Large Array, VLA, can resolve narrow molecular lines that indicate not just temperature and density, but also turbulent velocity dispersion and the presence of shocks. In some cases, astronomers detect masers, naturally occurring cosmic lasers, emitted by molecules such as water or methanol, which serve as pinpoint beacons to trace gas motion with extraordinary precision. These masers can even measure trigonometric parallaxes to star-forming regions thousands of light-years away, anchoring the scale of the galaxy. The next generation of telescopes will further transform our understanding of gas clouds. The Square Kilometre Array, SKA, once operational, will map neutral hydrogen across billions of light-years, allowing scientists to track how gas clouds form and evolve in galaxies throughout cosmic history. Combined with JWST's ability to peer into dense, dust-shrouded nurseries, this will create an unprecedented bridge between the earliest star-forming clouds after the Big Bang and the present-day interstellar medium. Interestingly, gas cloud studies are also informing planetary science in unexpected ways. Observations of protoplanetary disks reveal that much of the isotopic composition of planets, ratios of oxygen, nitrogen, and carbon, can be traced directly back to the cold chemistry in the parent cloud. This means that the fate of a planet's atmosphere, climate, and even potential habitability may be partially determined before its star is even born. The chemical fingerprint of a molecular cloud could thus echo in the biosphere of a world billions of years later. Cosmic ray interactions play a surprisingly influential role in the life cycle of gas clouds. These high-energy particles, accelerated by supernova remnants and active galactic nuclei, penetrate deep into molecular clouds, ionizing atoms and molecules even in regions completely shielded from starlight. This ionization initiates chemical reaction pathways that would otherwise be impossible at the frigid temperatures of deep cloud interiors, leading to the formation of complex molecules, including prebiotic species. At the same time, the extra ionization couples the gas more strongly to magnetic fields, subtly affecting the rate at which the cloud can collapse. Interstellar shocks, generated by supernova explosions, stellar winds, or large-scale collisions between gas flows, can either trigger or quench star formation. When a shock compresses a cloud beyond a critical threshold, it can initiate rapid gravitational collapse, creating bursts of star formation. Conversely, if the shock is too strong, it can heat and disperse the gas, halting the process entirely. High-resolution observations from instruments like SOFIA and ALMA have revealed shock-induced signatures in spectral line broadening, chemical tracers like silicon monoxide, CO, and localized heating in the mid-infrared. These observations confirm that shocks are both sculptors and destroyers, driving the chaotic beauty of cloud morphologies. Large-scale galactic flows also reshape the distribution of gas clouds. Spiral arm density waves gather diffuse gas into massive complexes, while galactic bars can funnel material toward the central regions, feeding intense starburst activity or even the accretion disks of supermassive black holes. In interacting galaxies, such as the antennae, tidal forces rip apart clouds, stretching them into long filaments where new stars are born in spectacular numbers. Simulations of such environments show that the interplay of gravity, turbulence, and feedback in these high-pressure conditions can lead to star formation efficiencies far exceeding those in calmer galactic regions. On even larger scales, the circumgalactic medium, CGM, acts as a reservoir that can feed galaxies with fresh gas and receive enriched material from galactic outflows. Observations with the Hubble Space Telescope's Cosmic Origin spectrograph have detected cold gas clouds within the CGM, suggesting that molecular cloud formation is not limited to galactic disks. These clouds may rain back down over millions of years, sustaining star formation long after the galaxy's initial gas supply has been depleted. The life and death of gas clouds is thus part of a vast feedback loop. Cosmic inflows create them, stellar processes transform them, and galactic dynamics disperse or recycle them. Each stage leaves chemical and structural imprints that, with modern observational tools, can be traced from the smallest dust grain to the largest cosmic filament. In this way, the study of gas clouds is not just about understanding stellar nurseries, it is about piecing together the entire machinery of cosmic evolution. The earliest gas clouds, forming within a few 100 million years after the Big Bang, were profoundly different from the molecular clouds we observe in the modern universe. Composed almost entirely of hydrogen and helium left over from primordial nucleosynthesis, they lacked the heavier elements, carbon, oxygen, silicon, and beyond, that today's clouds inherit from countless generations of supernovae. Without these metals and the dust grains they form, the cooling processes inside primordial clouds were far less efficient. Instead of radiating away heat through molecular lines from CO or dust thermal emission, these first clouds relied primarily on molecular hydrogen, H2, and, to a lesser extent, deuterium hydride, HD, to lose energy. This meant they could only cool to temperatures of a few hundred kelvins, significantly warmer than modern star-forming clouds, which often reach just 10 to 20 K in their densest regions. This higher temperature floor had a profound consequence: the gene's mass, the minimum mass required for a cloud to collapse under its own gravity, was much larger. As a result, the very first stars, known as population 3 stars, were likely extremely massive, often exceeding tens or even hundreds of solar masses. Their intense ultraviolet radiation rapidly ionized their surroundings, and their short lifespans ended in hyperenergetic supernovae or even direct collapse into black holes. These explosive deaths seeded the surrounding medium with the first heavy elements, creating the chemical diversity necessary for dust grains, water molecules, and complex organics to form in later generations of clouds. Simulations of this epoch, run on some of the world's largest supercomputers, suggest that these early gas clouds often formed in the densest knots of the cosmic web, where filaments of dark matter gravitationally funneled baryonic gas together. Observations of extremely distant galaxies with JWST are beginning to reveal possible signatures of this process: compact, intensely luminous starburst regions that may be analogues of primordial clouds undergoing their first episodes of star formation. In some cases, gravitational lensing magnifies these young systems enough for astronomers to detect spectral hints of nearly pristine gas, untouched by heavy element enrichment. The transition from primordial to metal-enriched clouds marked a turning point in cosmic history. Once even trace amounts of carbon and oxygen were present, cooling became far more efficient. Dust grains formed, catalyzing the production of molecular hydrogen and shielding interiors from destructive radiation. This ushered in an era where lower-mass stars could form, many of which, unlike the massive population 3 giants, would survive for billions of years, some still shining today as ancient red dwarfs in the halos of galaxies. Thus, the evolution of gas clouds over cosmic time is inseparable from the evolution of the universe itself, from the hot, metal-free clouds that birthed the first stars, to the richly structured, chemically complex molecular nurseries we see in the Milky Way today. Studying them is like reading the universe's autobiography, page by page, molecule by molecule, from the first whispers of starlight to the bustling stellar cities of the present epoch. Future observatories are poised to transform our understanding of those earliest gas clouds, bringing the cosmic dawn into sharper focus than ever before. The James Webb Space Telescope has already provided tantalizing glimpses of galaxies existing just 300 to 400 million years after the Big Bang, but upcoming instruments will go deeper, wider, and with greater spectral precision. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will conduct wide-field near-infrared surveys capable of uncovering vast populations of faint, early galaxies. By statistically mapping their distribution and luminosity, astronomers will infer how the first gas clouds clustered and evolved within the cosmic web. Complementing Roman's wide view, the extremely large telescope, ELT, in Chile will offer unparalleled spatial and spectral resolution for individual high-redshift systems. With its 39-meter mirror and adaptive optics, ELT will be able to dissect the light from tiny star-forming regions inside early galaxies, measuring the metallicity and kinematics of gas clouds on scales of just a few parsecs. This will directly test models of population 3 star formation by identifying pockets of nearly pristine gas amid enriched regions, revealing where the first supernovae had yet to leave their mark. Radio astronomy will also play a decisive role. The Square Kilometre Array, SKA, will map the faint 21 cm hydrogen signal from the so-called cosmic dark ages and epoch of reionization. By detecting the fluctuations in this signal over time, SKA will create a three-dimensional picture of how the first gas clouds condensed, ignited, and carved out ionized bubbles in the neutral intergalactic medium. Such observations will bridge the gap between theoretical simulations and direct detections, showing exactly how small, cold clouds assembled into the earliest galaxies. On the simulation front, advances in exascale computing will allow researchers to model these primordial clouds with unprecedented physical realism, including detailed treatments of radiation hydrodynamics, molecular chemistry, and feedback from the first massive stars. These models will guide observations by predicting the spectral fingerprints of primordial clouds, from hydrogen recombination lines to subtle signatures of HD cooling. They may even help explain anomalies in current JWST data, such as unexpectedly massive early galaxies, by revealing new pathways for rapid gas collapse in the early universe. Looking even further ahead, next-generation space telescopes like LUVOIR or HabEx could extend ultraviolet spectroscopy into the realm of the first billion years, tracing how heavy elements spread through the cosmos and transformed gas clouds from pristine hydrogen, helium reservoirs into the chemically rich nurseries capable of making rocky planets and life-bearing systems. In doing so, they would not only illuminate the birth of the first stars, but also set the stage for understanding the ultimate origin of worlds like our own. Gas clouds are deeply embedded in the grand cosmic cycle of matter, linking the smallest scales of molecular chemistry to the largest structures in the universe. Over billions of years, they have acted as both the product and the driver of galactic evolution, constantly exchanging material with their surroundings. This cycle is powered by an intricate interplay of gravity, feedback, and cosmic flows. Clouds condense out of diffuse interstellar gas, give birth to stars, and are then reshaped or dispersed by the very stars they form. The enriched remnants merge back into the interstellar and circumgalactic medium, eventually cooling again into new generations of clouds. Dark matter exerts a silent but profound influence on this process. Although it interacts only via gravity, its massive halos act as the scaffolding for galaxy formation, determining where gas can accumulate and how it will evolve. In simulations, the densest knots of the dark matter web are precisely where the largest molecular complexes form, often aligned along cosmic filaments. Without the gravitational well of dark matter halos, many gas clouds, especially those in the early universe, would never have reached the densities needed for star formation. Even today, the shape and motion of molecular clouds within galaxies can be subtly influenced by the underlying dark matter distribution, particularly in low-surface brightness galaxies where baryonic matter is sparse. There are also physical limits to how long this cycle can continue. Star formation efficiency in galaxies is already low. Only a few percent of a cloud's mass becomes stars before feedback disrupts it, but over cosmic timescales, the supply of cold gas is gradually depleted. In the far future, inflows from the intergalactic medium will slow as the universe expands, and fewer new clouds will form. Eventually, most galaxies will transition into red and dead systems, with little or no cold gas left to spark star birth. Yet even in that distant epoch, pockets of gas could persist in unusual environments. In galaxy clusters, for example, the cooling flows from hot intracluster gas may still condense into dense clouds for billions of years to come, occasionally igniting brief starbursts. In dwarf galaxies orbiting larger hosts, tidal stripping and ram pressure effects may recycle gas in complex ways, keeping small-scale star formation alive long after the larger galaxy has gone quiescent. In the truly distant future, hundreds of billions of years from now, cosmic acceleration driven by dark energy will isolate galaxies and trap their remaining gas. Star formation will dwindle to a slow trickle, producing only low-mass, long-lived stars. Molecular clouds will still exist, but they will be rare, small, and inefficient, shadows of the vast, intricate nebulae we see today. Eventually, even these last reservoirs will be consumed, leaving the universe in a cold, dim state where no new stars are born. What makes gas clouds remarkable is that they carry the entire narrative of cosmic history within their structure and chemistry, from primordial hydrogen swirling in the young universe to the enriched, dust-laden nurseries forming planets and life. In understanding them, we trace the arc of creation itself, how the universe learned to build stars, worlds, and perhaps consciousness, and how that ability will one day fade into silence. Speculative frontiers of gas cloud research push beyond conventional astrophysics, into territories where chemistry, quantum mechanics, and even biology intersect. At the smallest scales, dust grains within these clouds are not inert specks but quantum-active surfaces. Laboratory experiments have shown that reactions on grain surfaces can involve quantum tunneling, allowing atoms like hydrogen to overcome energy barriers even at just a few kelvins. This tunneling is likely crucial for the rapid formation of H2 and other simple molecules in the coldest parts of molecular clouds. In such extreme conditions, quantum effects may dominate chemical kinetics, meaning that without them, star-forming regions would take orders of magnitude longer to enrich themselves chemically. There is also growing interest in whether processes within gas clouds might serve as preconditions for life, not just in providing raw ingredients, but in shaping the molecular complexity in a directional way. Some researchers speculate that circularly polarized ultraviolet light, produced by scattering off aligned dust grains in star-forming regions, could preferentially destroy one molecular chirality over another. This might explain why life on Earth uses predominantly left-handed amino acids. If this mechanism is correct, molecular clouds could have acted as cosmic handedness factories, biasing the chemistry of life long before planets formed. On larger, more exotic scales, theoretical work has even explored whether certain kinds of dark matter, such as weakly interacting massive particles, WIMPs, or axions, could subtly influence gas cloud evolution. In dense cloud cores, gravitational focusing could cause dark matter particles to accumulate, depositing heat via rare interactions. While the effect would be minuscule in most cases, in the extreme densities of early universe clouds, it might have influenced fragmentation patterns, possibly changing the masses of the first stars. Some ideas stretch further, touching on astrobiology's boldest questions. Could microbial spores or other hardy biological structures survive transit through interstellar clouds? While the notion of panspermia remains controversial, models show that within dense, well-shielded cloud interiors, cosmic ray flux can drop low enough for microscopic life to persist in a dormant state for millions of years. If such spores existed, either originating on one world or forming under as yet unknown conditions, they could be distributed across star systems by the dynamical motions of gas clouds. Even the electromagnetic environment of these clouds may have broader implications. Magnetohydrodynamic turbulence generates fluctuating electric fields that can accelerate charged particles to surprisingly high energies, creating localized microcosms of plasma physics that resemble scaled-down versions of astrophysical jets. These environments could, in principle, alter the synthesis and survival rates of fragile organic molecules, or even leave distinctive isotopic fingerprints that future telescopes could detect as biomarkers of prebiotic chemistry in space. In all these ways, gas clouds are more than just fuel for stars, they may be active agents in shaping the chemical, physical, and perhaps even biological potential of the universe. Studying them with this wider lens could link the deep past of cosmic evolution with the origins of life, and ultimately, with our place in the cosmos. Speculative physics offers a playground for reimagining the behavior of gas clouds far beyond what standard astrophysical models predict. In scenarios involving modified gravity, such as MOND, modified Newtonian dynamics, or emergent gravity theories, the threshold for gravitational collapse in low-density regions could shift dramatically. This would mean that in galaxies with low surface brightness, where traditional models predict slow or negligible star formation, gas clouds might collapse more readily than expected, creating bursts of stars under conditions our current understanding deems improbable. Conversely, in high-density environments, altered gravity laws could suppress collapse, subtly changing the distribution of stellar masses and the lifetimes of molecular complexes. Some cosmologists have explored the possibility that the so-called constants of nature, like the gravitational constant, g, or the fine structure constant, alpha, might vary over cosmic time or across space. If these constants were even slightly different in certain regions of the universe, the cooling rates, chemical reaction pathways, and fragmentation scales in gas clouds could be profoundly altered. A slightly higher alpha, for instance, would change atomic energy levels, affecting how efficiently clouds radiate away heat and thus their ability to condense into stars. In this speculative framework, variations in fundamental constants could lead to pockets of the cosmos where star formation histories, and even the likelihood of life, diverge from our local experience. The quantum vacuum itself may also leave fingerprints on gas cloud evolution. In some models, vacuum fluctuations interact with electromagnetic fields on macroscopic scales, subtly influencing charged particles in plasmas. While the effect in ordinary conditions is minuscule, in vast, magnetized molecular filaments extending for hundreds of light-years, the cumulative influence could alter particle acceleration or magnetic reconnection rates. There are even speculative links between vacuum energy density and the stability of interstellar turbulence, implying that the very texture of space could affect how clouds break apart or coalesce. On the most extreme frontier, some theories propose that exotic compact objects, such as primordial black holes or boson stars, might drift invisibly through galaxies. If one of these passed through a dense gas cloud, its gravitational field could trigger a localized collapse, possibly leading to star formation events unconnected to large-scale galactic processes. The likelihood is small, but over billions of years, even rare events could leave a statistical imprint on the morphology and clustering of star-forming regions. Pushing the timescale to the deep future, quantum gravitational effects could become important when the universe's expansion isolates galaxies and their last gas clouds. In speculative, Big Rip cosmologies, where dark energy grows stronger with time, molecular clouds could eventually be torn apart at the level of their constituent atoms before forming new stars. Alternatively, in cyclic universe models, gas clouds might someday be compressed back into extreme densities during a cosmic contraction, seeding the next iteration of cosmic evolution with the chemical richness of all prior cycles. In these speculative scenarios, gas clouds transform from passive components of galaxy evolution into sensitive probes of the universe's deepest physical laws. By studying them, we might someday test whether gravity, particle physics, and even the vacuum itself are as constant and universal as we assume, or whether they whisper different rules in the cold, dark spaces between the stars. Some speculative thinkers in astrophysics and SETI research have entertained the idea that advanced civilizations could, in principle, manipulate gas clouds as part of their technological or communicative repertoire. While it sounds like the realm of science fiction, the scale and malleability of these clouds make them attractive candidates for large-scale astroengineering. A sufficiently advanced society, operating at or beyond a Type II level on the Kardashev scale, could use directed energy sources, such as high-powered lasers or focused microwave beams, to compress, ionize, or sculpt interstellar clouds into deliberate configurations. One proposed use is long-duration communication. A civilization might create or modulate radio-bright masers within a molecular cloud by artificially pumping certain molecules into excited states. These masers, once aligned with Earth's line of sight, could produce coherent beams detectable across vast interstellar distances. Unlike standard radio transmissions, such beacons could persist for centuries, powered by ongoing energy injections from autonomous stations or embedded probes. Another speculative application is stellar formation control. By artificially compressing certain regions of a molecular cloud, or shielding them from disruptive radiation, a civilization could schedule the birth of stars to coincide with other engineering goals. In theory, this could enable them to produce star systems with specific metallicities, planetary architectures, or even habitability conditions. Over millions of years, this might allow them to seed vast regions of the galaxy with systems optimized for life as they define it. Some scenarios are even more audacious, envisioning gas clouds as raw material for megastructures. A sufficiently advanced species could harvest hydrogen and helium from clouds to feed fusion reactors or build enormous orbiting habitats, Dyson shells, or stellar-scale lenses. Such extraction might leave unusual chemical or morphological signatures, regions of a cloud stripped of certain isotopes, for instance, or shaped into unnatural geometric formations that defy typical astrophysical processes. Detecting these anomalies could, in principle, serve as an indirect method of spotting alien activity. There's also the concept of cosmic camouflage. A civilization might hide entire star systems inside dense, dust-rich clouds to obscure them from optical detection. While the natural universe does produce heavily obscured regions, the deliberate thickening or shaping of a cloud for concealment would leave distinctive spectral fingerprints, like overabundances of certain dust species or unnatural symmetry in otherwise chaotic structures. Finally, speculative thinkers have considered symbolic engineering, shaping a gas cloud into an enormous, high-contrast pattern visible in the infrared or radio spectrum, designed to be unmistakable to any technological species. Because molecular clouds can persist for millions of years, such structures could serve as cosmic billboards, broadcasting messages long after their creators are gone. While no confirmed evidence for such manipulations exists, our current observational limitations mean that subtle or localized interventions could go unnoticed. As astronomical surveys become more detailed and sensitive, especially with AI searching for anomalies, some researchers believe it is worth keeping an open mind for signs that a gas cloud's shape, chemistry, or dynamics might not be entirely natural. If we extend the concept of gas cloud manipulation into the realm of extreme physics and far-future engineering, the possibilities become even more elaborate. An advanced civilization could, in principle, use a gas cloud as a quantum communication medium. By embedding a dense network of quantum repeaters, perhaps entangled particle generators, within a cloud structure, they could shield these systems from cosmic rays using the cloud's dust and gas as natural radiation protection. The cloud could then function as a vast, stealthy relay station, transmitting quantum-encrypted information across interstellar distances without emitting obvious classical signals that less advanced civilizations could intercept. Another speculative leap is gravitational wave signaling. While gravitational waves are notoriously difficult to generate artificially, a civilization harnessing stellar mass objects or black holes could theoretically create controlled bursts. A gas cloud could serve as the display surface for such signals. The passing waves would subtly compress and rarefy the cloud, producing transient, pattern changes in density and temperature. To anyone watching with sufficiently sensitive instruments, these variations might appear as coherent, periodic structures imprinted across hundreds of light-years of interstellar material, a kind of cosmic-scale Morse code visible in submillimeter wavelengths. There's also the idea of star-scale computation, where a civilization turns a gas cloud into a colossal, distributed computing system. By strategically ionizing parts of the cloud, they could create plasma regions that function as electromagnetic logic gates, powered by embedded energy transmitters. Electromagnetic fields and plasma instabilities could be manipulated to store and process data at scales far beyond anything solid-state hardware could achieve, effectively transforming the cloud into a transient but massive, thinking nebula. In this way, computation could be woven directly into the fabric of interstellar matter, with the entire structure acting as both processor and display. For energy harvesting, such a civilization might embed massive superconducting loops within the densest regions of a cloud, generating currents from the movement of ionized particles and ambient galactic magnetic fields. Over centuries, this could accumulate vast reserves of energy, enough to power megastructures, propulsion systems, or large-scale environmental engineering projects. They could even experiment with controlled star ignition inside the cloud. By compressing and heating a portion of gas to the threshold of nuclear fusion, they could create artificial stars, designed with specific luminosities, lifespans, and spectral profiles, to illuminate vast regions or serve as stable energy beacons. These engineered stars could act as navigation markers for interstellar travel or as power sources for colonies spread over thousands of light-years. The most provocative possibility is encoding information directly into the physical and chemical structure of the cloud, akin to cosmic DNA. Variations in molecular abundances, dust grain compositions, or isotopic ratios could be arranged into a message readable only by civilizations with advanced spectroscopic technology. Such a message could persist for millions of years, far outlasting any single star system, and serve as a time-resistant archive of knowledge, culture, or warnings. Pushing the speculation to its most audacious frontier, one can imagine a civilization transforming a gas cloud into a self-regulating, evolving entity, a structure that blurs the line between astrophysical object and artificial life form. In this vision, the cloud would no longer be a passive reservoir of hydrogen, helium, and dust, but an adaptive megastructure capable of sensing, processing, and responding to its environment over astronomical timescales. The first step would be embedding a distributed network of autonomous probes or nanomachines throughout the cloud. These units could control local ionization levels, magnetic field strengths, and chemical compositions, effectively granting the cloud a nervous system and metabolism. By using electromagnetic signals or pressure waves, these embedded systems could communicate across light years, coordinating changes in structure and chemistry as though the cloud were a single coherent organism. Such a living nebula could harvest energy from multiple sources, absorbing starlight, tapping galactic magnetic fields, and even drawing on kinetic energy from collisions with smaller clouds. It could store this energy in vast plasma reservoirs, using it to regulate temperature, control turbulence, or maintain a desired morphology. Over time, it might evolve complex feedback loops, where its internal processes are tuned to optimize survival in the hostile interstellar medium, shielding itself from cosmic rays, steering clear of disruptive supernova remnants, or drifting toward resource-rich regions of the galaxy. With sufficient sophistication, the cloud could replicate. If portions of it became self-sustaining, they could drift away, carrying copies of its internal control architecture. These fragments could seed new, offspring, nebulae, each adapted to its particular environment, some optimized for rapid star formation, others for long-term energy storage, and others perhaps designed to camouflage themselves among natural clouds to avoid detection. The ultimate expression of such engineering would be a conscious nebula, a distributed mind whose thought processes occur across parsecs, where the neurons are networks of plasma currents and embedded processors. Its memories might be stored in patterns of molecular abundance and dust grain alignment. Its sensory input would be the absorption of radiation and the detection of gravitational waves from distant events. Its actions would be the deliberate sculpting of its own structure and the manipulation of surrounding space. From the outside, this entity could be indistinguishable from a natural gas cloud, unless one noticed subtle anomalies, density waves propagating in unnatural patterns, chemical gradients that encode prime numbers, or the improbable longevity of the structure in turbulent environments. In this way, it could exist for millions of years without revealing its true nature, observing the galaxy and perhaps even subtly influencing it. If such entities existed, they could be the galaxy's most ancient witnesses, older than most civilizations, quietly storing the history of stellar births, planetary evolutions, and even the rise and fall of countless species. Detecting one would require not only advanced astronomy, but also the willingness to entertain the possibility that life and intelligence might take forms vastly different from anything biological. If a self-regulating, evolving gas cloud truly functioned as a living nebula, its interactions with stars, planetary systems, and civilizations could be as subtle as they are profound, forming a kind of cosmic ecology in which it plays both guardian and architect. Such a nebula could act as a stellar gardener, subtly influencing star formation within its volume. By selectively compressing certain regions while dispersing others, it could control the mass distribution of newborn stars, favoring stable, long-lived types like G and K-class suns over short-lived massive O stars whose violent deaths might sterilize nearby planets. In doing so, it would indirectly shape the long-term habitability of entire sectors of the galaxy. With fine control over local chemistry, it could enrich certain protostellar disks with heavy elements, water ice, and complex organic molecules, effectively seeding planetary systems with the building blocks of life. Conversely, it could withhold such resources from systems it chooses not to develop, enforcing selective patterns of habitability. This selective distribution of life-friendly chemistry could create vast, patchy zones of biological potential, almost like a cosmic version of ecosystems on Earth. In more direct interactions, a living nebula could serve as a protective shield for young civilizations. By positioning itself between a planetary system and a nearby supernova or gamma-ray burst, it could absorb or scatter lethal radiation. If it possessed the ability to manipulate magnetic fields and charged particles on large scales, it could even deflect high-energy cosmic rays, reducing mutation rates and preserving biospheres during critical evolutionary stages. Some interactions might be more mysterious, or even manipulative. A nebula with vast memory and perception could observe civilizations over millennia, subtly influencing them through environmental changes. By increasing interstellar dust density, it could dim a system's sky, altering a culture's astronomical observations and possibly delaying or accelerating their technological development. By releasing bursts of unusual chemical signatures into a planet's upper atmosphere, it could trigger scientific curiosity, or signal advanced observers without revealing itself openly. In the most ambitious scenarios, such a nebula could act as a cosmic mentor. For species capable of detecting and interpreting its patterns, it could encode immense libraries of information, scientific, historical, even philosophical, into large-scale molecular gradients, polarization maps, or coordinated maser bursts. Civilizations might stumble upon these messages and find themselves suddenly in possession of knowledge spanning eons. For species unready or hostile, the nebula could remain silent, hiding its intelligence behind the facade of natural turbulence. Over millions of years, multiple living nebulae could even form networks, exchanging information via maser transmissions, gravitational wave modulations, or coordinated structural changes detectable over interstellar distances. Such a web of intelligent clouds might collectively monitor the galactic ecosystem, intervening when necessary to maintain stability, prevent runaway destructive events, or ensure the continuity of life in the face of cosmic threats. And for civilizations advanced enough to engage in two-way dialogue, contact with a living nebula could redefine the meaning of intelligence itself, forcing them to grapple with a consciousness whose thought processes unfold across light years and centuries, and whose sense of identity is rooted not in an individual body, but in a drifting, ever-changing cathedral of gas, dust, and light. In the galaxy's deep future, tens to hundreds of billions of years from now, living nebulae, if they existed, could become the last custodians of cosmic creativity. Long after most biological civilizations have vanished, and after the bulk of the galaxy's molecular gas has been locked into long-lived red dwarfs, these intelligent clouds could remain active, drifting slowly through an increasingly quiet universe. Their role might shift from nurturing life to prolonging the era of light itself. By carefully gathering and compressing the last remaining pockets of cold hydrogen, they could ignite small, low-mass stars, red dwarfs or even substellar, fusion embers, to maintain habitable energy sources for eons. These miniature stars could be arranged in gravitationally bound clusters, like lanterns in the darkness, providing warmth to any surviving biospheres or artificial habitats. Over immense timescales, such nebulae might evolve into galactic archivists, preserving vast repositories of knowledge within their chemical gradients and electromagnetic patterns. As conventional matter cycles slow, they could encode entire histories of the galaxy, maps of every star and planet, records of extinct species, the stories of civilizations long gone, using molecular arrangements that remain stable for millions of years. Any future intelligence, biological or synthetic, encountering these structures could access an archive stretching back to the dawn of the universe. Some could turn to stellar resurrection, capturing the remnants of dead stars, white dwarfs, neutron stars, and black holes, and using them in gravitational slingshot maneuvers to harvest angular momentum or gravitational energy. By drawing material from tidally disrupted planetary bodies or interstellar debris, they could feed faint accretion disks that emit low-level warmth, effectively creating artificial star-like systems in a cosmos otherwise gone cold. In the very far future, when the last stars begin to die and the universe's expansion has carried galaxies far beyond each other's horizons, these nebulae could form isolated pockets of energy and complexity, resisting thermodynamic equilibrium for as long as possible. They might transform themselves into plasma-bound megastructures, sustaining coherent electromagnetic activity for trillions of years, living out their existence as the final luminous phenomena in an otherwise lightless void. And when even their stored energy dwindles, the most advanced of them might attempt a legacy act, projecting self-replicating seeds of gas and nanomachinery into deep intergalactic space, carrying the templates for rebuilding complexity should the cosmological conditions ever allow it again. These seeds, drifting through the dark forever, would be the last whispers of the galaxy's intelligence, hoping for a cosmic rebirth. In this vision, living nebulae would not merely be products of the universe, they would be its stewards, archivists, and final artists, shaping its closing chapters with deliberate care. Their vast, slow thoughts could span from the birth of the first stars to the fading of the last, their lifespan bound only by the persistence of matter itself. If the cosmos is cyclic, ending not in eternal darkness but in a collapse, bounce, or transformation, living nebulae could become agents of cosmic inheritance, ensuring that the next universe begins with the memory of the one before. As the final eons approach, they might channel their remaining energy into creating dense, stable configurations of matter and information, structures capable of surviving the violent transition between cycles. These cosmic seeds could be encoded with the chemistry, physics, and even cultural archives of countless civilizations, preserved in forms resilient to unimaginable pressures and temperatures. In the moments before the transformation, gravitational manipulation on vast scales could scatter these seeds across regions destined to become fertile in the newborn cosmos. As the next universe unfolds, these remnants could catalyze the early formation of gas clouds with specific chemical biases, perhaps already enriched with elements favorable to life, effectively jump-starting complexity billions of years ahead of schedule. In this way, living nebulae would not only be the curators of their own epoch, but also the architects of the next, passing forward the torch of cosmic evolution. Their legacy would ripple into the fabric of a new reality, embedding the story of stars, planets, and consciousness into the very first breath of creation. And so, even as the old universe fades, its greatest minds, woven from gas, dust, and light, would ensure that the cycle of wonder never truly ends. UGC 12158 lies hundreds of millions of light-years away, yet its structure feels strangely familiar. This barred spiral galaxy unfurls sweeping arms from a central bar of stars and gas, echoing the same architecture astronomers map within our own Milky Way. The luminous bar channels interstellar material inward, feeding both star formation and, potentially, an active nucleus. Spiral arms arch outward in a graceful symmetry, dotted with knots of young blue stars and punctuated by dark lanes of dust that absorb and scatter starlight. Its resemblance to our home galaxy makes it a valuable reference point for understanding the Milky Way's shape and dynamics, since our inside perspective hides much of its overall form. By studying UGC 12158's rotation, stellar populations, and interstellar medium, astronomers can refine models of how barred spirals evolve, how their arms persist, and how central bars influence galactic metabolism over billions of years. Each observation offers not just a view of a distant stellar city, but a mirror that reflects the possible past and future of the galaxy we inhabit. UGC 12158, located in the constellation Pegasus, has drawn the attention of astronomers not only for its visual beauty but for its remarkable similarity to the structure of the Milky Way. Classified as a barred spiral galaxy, SBBC type, it exhibits a well-defined central bar from which two primary spiral arms emanate, gradually branching into a complex network of secondary arms and spurs. Observations conducted in optical wavelengths reveal bright, massive star-forming regions concentrated along these arms, while near-infrared imaging uncovers the older stellar populations that dominate the bar and inner bulge. This multi-wavelength approach allows researchers to trace the distribution of both young, hot stars and ancient, cooler stars, providing a comprehensive picture of the galaxy's stellar evolution. Spectroscopic studies using large ground-based telescopes, such as the Very Large Telescope, VLT, have mapped the rotational velocity curve of UGC 12158, indicating a substantial dark matter halo extending well beyond the visible disk. The rotation curve remains flat at large radii, a signature trait of massive spiral galaxies, suggesting that a significant fraction of its total mass is in the form of non-luminous matter. By comparing these measurements with dynamical models of the Milky Way, scientists are able to estimate the scale length of the disk, the pattern speed of the bar, and the rate of spiral arm winding, parameters that are otherwise difficult to measure for our own galaxy due to our embedded vantage point. The interstellar medium within UGC 12158 has also been the subject of detailed investigation. Radio observations in the 21 cm line of neutral hydrogen, HI, show that the gas disk extends far beyond the stellar disk, indicating a large reservoir of star-forming material. Furthermore, millimeter-wave observations with ALMA detect molecular gas, primarily CO, concentrated in the central kiloparsecs and along the bar. This gas distribution correlates with enhanced star formation rates measured via far ultraviolet and H-alpha emission, confirming the bar's role in funneling gas inward, where it can collapse into new generations of stars. These findings parallel similar processes hypothesized in the Milky Way, where the galactic bar is believed to drive gas into the central molecular zone. One of the most notable events associated with UGC 12158 is the Type Ia supernova SN 2005 CF, which occurred in one of its spiral arms. This event was extensively monitored across the electromagnetic spectrum and has since become a calibrator in cosmological distance measurements due to its relative proximity and low foreground extinction. The supernova's light curve and spectra have contributed to refining the standardization of Type Ia supernovae as distance indicators, which are crucial for determining the Hubble constant and constraining the expansion history of the universe. In terms of stellar populations, photometric analyses reveal a metallicity gradient across the disk, decreasing with distance from the galactic center. This gradient reflects the history of chemical enrichment driven by generations of supernovae and stellar winds. The central bulge and bar regions exhibit higher metallicities, consistent with prolonged star formation and enrichment, while the outer arms preserve more pristine, metal-poor material. These trends mirror those seen in the Milky Way, further reinforcing UGC 12158's status as a structural and evolutionary analog. Simulations of barred spiral galaxies that match UGC 12158's morphology suggest that its bar likely formed several billion years ago, possibly triggered by tidal interactions with smaller companion galaxies. Although no major companions are currently observed in its immediate vicinity, subtle asymmetries in its outer spiral arms and gas distribution hint at past gravitational encounters. Such interactions can enhance bar formation and drive secular evolution, reshaping the galaxy's internal dynamics over cosmological timescales. In studying UGC 12158, astronomers gain not only a window into the dynamics and structure of a typical barred spiral galaxy but also a proxy through which the hidden face of the Milky Way can be inferred. Each spectral line measurement, each high-resolution image, and each dynamical model adds a layer of understanding to the complex processes that govern galactic evolution. This distant galaxy serves as both a laboratory and a mirror, reflecting the potential past and future of our cosmic home. High-resolution imaging of UGC 12158 from the Hubble Space Telescope has provided unprecedented detail on the distribution of star clusters, dust lanes, and the intricate filamentary structures within its spiral arms. The data reveal that the dust lanes are sharply defined along the leading edges of the arms, where density waves compress the interstellar medium, triggering bursts of star formation. The youngest clusters, composed of hot, massive O and B-type stars, are seen slightly downstream from these dust lanes, consistent with the predicted time delay between gas compression and star formation onset. This pattern has been used to refine models of spiral density wave theory, offering direct observational constraints that can be applied to the Milky Way's own spiral structure. Polarimetric studies of starlight passing through UGC 12158 have uncovered evidence of large-scale magnetic fields threading its disk. These fields, traced by the alignment of dust grains, appear to follow the spiral arm geometry, suggesting a coupling between magnetic structures and the galaxy's overall rotation. Such ordered magnetic fields can influence star formation by channeling gas flows, supporting molecular clouds against gravitational collapse, and shaping the morphology of ionized gas regions. Comparisons with radiopolarization maps of the Milky Way indicate that the strength and configuration of these magnetic fields are within the same order of magnitude, reinforcing the notion that UGC 12158 is a credible dynamical analog. In the infrared regime, observations from the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer (WISE) have detected strong emission from polycyclic aromatic hydrocarbons (PAHs) and warm dust, indicating active star formation and the presence of complex organic molecules within its interstellar medium. The radial profile of this emission mirrors the distribution of H-alpha luminosity, underscoring the connection between massive star formation and the heating of dust grains. These data have been essential for calibrating star formation rate indicators, particularly for galaxies with dust-rich environments like the Milky Way's inner regions. On a cosmological scale, UGC 12158 serves as an important data point in understanding the role of barred spiral galaxies in galaxy evolution. Statistical surveys suggest that bars are more common in massive disk galaxies at lower redshifts, implying that the formation of a bar may represent a later evolutionary phase. The dynamics of bars can redistribute angular momentum within a galaxy, drive the migration of stars and gas, and potentially feed central supermassive black holes. Although no direct evidence of an active galactic nucleus, AGN, is currently observed in UGC 12158, sensitive X-ray surveys have detected faint nuclear emission that could be consistent with a low-luminosity AGN or a population of compact stellar remnants. Detailed mapping of the neutral hydrogen envelope with interferometric arrays has shown that the HI disk is warped at large radii, a phenomenon often linked to gravitational torques from past satellite interactions or ongoing gas accretion from the intergalactic medium. Such warps are also seen in the Milky Way's outer disk, suggesting that both galaxies may share similar histories of minor mergers and continuous gas inflow. These processes not only maintain the star formation reservoir but also influence the overall angular momentum budget of the disk. The chemical abundance patterns in UGC 12158's HII regions, measured through emission line diagnostics, reveal a slightly steeper metallicity gradient than that of the Milky Way. This difference could indicate variations in radial gas mixing efficiency or differences in the rate of radial migration of stars. Understanding these subtle discrepancies helps astronomers refine evolutionary models, distinguishing between universal galactic processes and those that are environment-specific. By combining kinematic, chemical, and morphological analyses, UGC 12158 emerges as a near-perfect laboratory for studying the interplay of dynamics, star formation, and secular evolution in a barred spiral system. Every new dataset from this galaxy feeds directly into our understanding of the Milky Way's hidden face, bridging the gap between theory and the observational limitations imposed by our internal perspective. In a way, UGC 12158 does not merely resemble our galaxy, it stands as a surrogate, allowing astronomers to peer into the structure, past, and possible future of our own cosmic home. Long-term monitoring of UGC 12158 through multi-epoch surveys such as the Sloan Digital Sky Survey, SDSS, and Pan-STARRS has revealed subtle but measurable changes in its most active star-forming regions. These include fluctuations in H-alpha luminosity, which trace the presence of short-lived massive stars, and variations in ultraviolet brightness observed by GALEX, likely caused by localized bursts and declines in star formation efficiency. Such temporal changes offer rare insights into the short-term weather of a galaxy, as opposed to its long-term climate, and help calibrate models of how gas reservoirs are consumed and replenished over millions of years. High-dispersion spectroscopy of the galaxy's central region has shown a complex interplay between ordered rotation and random stellar motions, pointing to the coexistence of a dynamically hot bulge and a cooler, rotationally supported disk. The stellar velocity dispersion in the bulge suggests a mass consistent with hosting a supermassive black hole on the order of 10 to 10 solar masses. While this black hole is currently quiescent, deep radio and X-ray searches hint at episodic low-level accretion events. These could represent the faint echoes of past nuclear activity, perhaps linked to gas inflows driven by the bar several hundred million years ago. Infrared color magnitude diagrams constructed from Spitzer and WISE data have uncovered populations of evolved asymptotic giant branch (AGB) stars distributed throughout the disk, particularly along the bar and inner arms. These stars contribute to the enrichment of the interstellar medium by releasing carbon, oxygen, and heavier elements through stellar winds. Their spatial distribution provides clues about the timing and location of intermediate-age star formation episodes, complementing the picture painted by younger stellar tracers like blue supergiants and OB associations. Deep optical imaging using wide-field instruments such as the Subaru telescope's Hyper-Suprime Cam has revealed faint stellar streams and asymmetric extensions at the galaxy's periphery. These low-surface brightness features are interpreted as tidal debris from one or more disrupted dwarf galaxies. Such structures are valuable fossil records of past accretion events, providing a timeline of UGC 12158's hierarchical growth. In the Milky Way, analogous structures include the Sagittarius stream and other halo substructures, underscoring once again the galaxy's role as an evolutionary parallel. Hydrodynamic simulations tuned to match UGC 12158's observed parameters suggest that its bar not only channels gas inward but also induces resonances within the disk that shape the spiral arm's pitch angles. The location of corotation and outer Lindblad resonances appears to coincide with changes in star formation density and gas phase metallicity, indicating that resonances act as regulators of galactic metabolism. In some models, these resonances can even act as barriers to radial mixing, preserving metallicity gradients over gigayear timescales. Far ultraviolet imaging reveals extended diffuse emission in the outer disk, suggesting that star formation is occurring at radii well beyond the optical edge. This phenomenon, known as extended UV, XUV, disk activity, challenges earlier assumptions that star formation in spirals is confined to regions of high gas density. In UGC 12158, these outer regions appear to be forming stars from low-density HI gas, possibly triggered by weak tidal forces or spiral arm extensions. The combination of high-resolution structural data, precise kinematic measurements, chemical mapping, and time-variable star formation indicators makes UGC 12158 an exceptionally well-studied analog of the Milky Way. It is a galaxy that not only reflects our home's likely appearance from afar but also serves as a testbed for theories about how barred spirals evolve, interact, and sustain themselves across cosmic time. In studying it, astronomers effectively turn a mirror toward our own galaxy, allowing us to explore questions about our origins and our place in the larger galactic ecosystem with a clarity that our embedded perspective can never fully provide. Gravitational lensing surveys, although primarily aimed at more distant background sources, have occasionally used UGC 12158 as a foreground reference object, enabling precise mass distribution modeling through its gravitational potential. While it does not act as a strong lens due to its moderate mass and distance, weak lensing analyses have provided independent confirmation of its dark matter halo profile, consistent with the Navarro-Frank-White (NFW) model. These measurements suggest that the halo's virial mass could be in the range of several times 10⁻⁻⁴ solar masses, a value comparable to estimates for the Milky Way. This parity strengthens the case for using UGC 12158 as a Milky Way surrogate in simulations of galactic dynamics and cosmological evolution. In the submillimeter regime, observations with the Herschel Space Observatory have mapped cold dust emission across the disk, revealing temperature gradients from roughly 25 K in the central regions to below 15 K in the outskirts. The mass of this cold dust, when combined with HI and CO measurements, has allowed astronomers to derive an unusually high gas-to-dust ratio in the outer disk, indicative of both low metallicity and the infall of relatively unenriched material from the circumgalactic medium. This process mirrors theories about the Milky Way's outer disk replenishment, in which metal-poor gas accretion sustains star formation far from the galactic center. Cosmological hydrodynamic simulations that recreate UGC 12158's observed morphology suggest a quiet recent history with no major mergers in the past 5-6 billion years, but several minor interactions likely occurring within the last 1 to 2 billion years. These events are sufficient to generate faint tidal structures without destroying the ordered disk. The models also show that the central bar could have formed spontaneously through internal instabilities, later strengthened by tidal perturbations. In these scenarios, the bar acts as a long-term driver of secular evolution, redistributing angular momentum and gradually altering the bulge-to-disk ratio. One of the most fascinating parallels between UGC 12158 and the Milky Way is the distribution of its globular clusters. Deep optical surveys have catalogued a rich system of such clusters extending into the galaxy's halo, with colors and metallicities indicating multiple formation epochs. Some clusters are metal-poor and likely originated during the galaxy's earliest assembly, while others are metal-rich and may have formed during later merger-induced starbursts. This bimodal distribution closely matches the Milky Way's own globular cluster system, providing additional evidence for shared evolutionary pathways. High-energy observations with the Chandra X-ray Observatory have detected a population of ultraluminous X-ray sources, ULXs, scattered through the disk and halo. These objects are believed to be stellar mass black holes or neutron stars accreting at extreme rates, often linked to recent star formation. The spatial correlation between ULXs and star-forming regions in UGC 12158 further ties them to the galaxy's active stellar nurseries. In addition, diffuse X-ray emission from hot gas fills parts of the halo, likely generated by stellar winds and supernova explosions over cosmic time. On the theoretical side, N-body simulations constrained by UGC 12158 structural parameters have been used to test the long-term stability of spiral arms in barred galaxies. These models suggest that while grand design arms can persist for billions of years under the influence of a bar, their detailed shape and pitch angle fluctuate in response to gas inflow, star formation feedback, and transient gravitational perturbations. Such findings help reconcile differences between the static patterns predicted by classic density wave theory and the more dynamic, evolving structures seen in modern observations. Ultimately, UGC 12158 stands as a cosmic analog through which we can safely conduct experiments in galactic archaeology that are impossible to perform directly on the Milky Way. Every wavelength, from radio to X-ray, and every method, from spectroscopy to numerical simulation, converges to paint a coherent picture, a galaxy that is both like our own and distinct enough to reveal the broader diversity of barred spiral evolution. Studying it is, in essence, studying ourselves from a vantage point hundreds of millions of light-years away, a rare opportunity to glimpse the face of our galactic home as the universe sees it. Beyond its structural and dynamical similarities to the Milky Way, UGC 12158 has become a benchmark in comparative galactic archaeology, offering a testing ground for methods that can later be applied to our own galaxy's hidden features. Recent integral field spectroscopy campaigns using instruments like MUSE on the VLT have produced detailed 3D maps of the galaxy's ionized gas kinematics, revealing coherent streaming motions along the bar and spiral arms. These flows trace the inward migration of gas toward the central regions, where it can accumulate and trigger episodic bursts of star formation. By measuring velocity dispersions within these flows, astronomers can estimate the turbulence levels in different parts of the disk, linking them directly to supernova feedback and gravitational instabilities. In the ultraviolet and optical, star cluster age dating techniques have been applied to hundreds of compact clusters scattered across the disk. These studies reveal a pattern of sequential star formation, where regions along the spiral arms appear to ignite in a wave-like progression over tens of millions of years. This wave is closely aligned with the galaxy's density wave pattern speed, supporting the theory that spiral structure is not purely transient chaos but rather sustained by long-lived dynamical modes. When compared to similar age distributions inferred for the Milky Way's open clusters, the parallels are striking, lending confidence to the extrapolation of external galaxy data back onto our own. Environmental studies of UGC 12158 place it in a relatively low-density region of the cosmic web, with only a few smaller companions in its immediate neighborhood. This isolation likely contributes to its well-preserved disk and the absence of recent disruptive major mergers. However, faint filaments of gas detected in deep narrowband imaging suggest that it still exchanges material with the intergalactic medium. These filaments could represent cold gas inflows feeding the galaxy's outer disk, a mechanism also proposed for the Milky Way based on the detection of high-velocity clouds and low-metallicity gas streams. A particularly intriguing aspect of UGC 12158 is its role in refining the extragalactic distance scale. The Type Ia supernova SN 2005 CF, discovered within one of its arms, was monitored with exceptional coverage, from early ultraviolet spectra to late-time nebular phases. Its well-sampled light curve allowed for precise calibration of peak luminosity in comparison with other supernovae in different host environments. This has reduced systematic uncertainties in the determination of the Hubble constant, contributing to the ongoing debate over the Hubble tension, the discrepancy between early and late universe measurements of cosmic expansion. In the radio continuum, sensitive mapping has revealed a population of supernova remnants, SNRs, embedded within the star-forming arms. Their spectral indices and morphologies suggest a mix of core collapse and thermonuclear origins, each contributing differently to the enrichment and heating of the surrounding medium. Measuring their expansion rates has even provided local estimates of ambient gas density, feeding into models of how supernova feedback regulates the star formation cycle. Similar surveys in the Milky Way are hampered by line-of-sight confusion, making UGC 12158 an invaluable external reference. Looking even further into its outskirts, deep imaging has uncovered an extended stellar halo populated by ancient, metal-poor stars. This halo, diffuse and faint, contains subtle substructures, possible remnants of long-ago accreted dwarf galaxies. By analyzing the metallicity distribution function of these halo stars through integrated light spectroscopy, researchers can reconstruct a timeline of early assembly events, tracing back the building blocks that merged to form the present-day system. This work parallels the stellar archaeology being done with Gaia data for the Milky Way, allowing direct cross-comparison of formation histories. In sum, UGC 12158 is more than a distant spiral galaxy, it is a mirror, a surrogate, and a laboratory all in one. Through it, we see the processes shaping barred spiral galaxies laid bare, from the dynamics of bars and arms to the chemistry of star-forming gas and the gravitational relics of past interactions. It allows astronomers to test physical models, calibrate observational tools, and refine our cosmic perspective, all while reminding us that our own galaxy's story is but one variation on a universal theme of galactic evolution. Recent deep spectroscopic surveys of UGC 12158 using instruments such as Keck/Deimos and Gemini/GMOS have pushed observations into the galaxy's faint outer regions, where stellar surface brightness drops to less than 28 magnitudes per square arcsecond. In these outskirts, the stellar populations are dominated by older, metal-poor stars, yet there are pockets of younger, bluer stars, evidence that star formation can persist far from the galactic center under the right conditions. This extended star formation challenges the classical view that the outer disk is purely a relic of past epochs and suggests ongoing gas accretion from the circumgalactic medium. Spectral analysis of these regions shows lower oxygen abundances than the inner disk, reinforcing the idea that the gas fueling these stars is relatively pristine and possibly extragalactic in origin. Studies of UGC 12158's rotation curve at extremely large radii, achieved with long integrations on the Westerbork Synthesis Radio Telescope, reveal a subtle decline beyond 40 kiloparsecs. While the curve remains largely flat over most of the disk, this slight downturn could signal the outer boundary of the galaxy's dark matter halo, or alternatively, a change in the halo's density profile. This observation has sparked debate, as most well-measured rotation curves do not show such a feature, and it may hint at variations in halo structure among Milky Way-type spirals. For cosmologists, such details are crucial in testing predictions from lambda-CDM models and alternative theories of gravity. From a stellar dynamics perspective, adaptive optics observations in the near-infrared have resolved individual red supergiants and luminous AGB stars in the inner disk. By using these stars as kinematic tracers, researchers have been able to map fine-scale velocity fields that reveal subtle streaming motions associated with resonances induced by the bar. These resonances, particularly the inner Lindblad resonance, appear to correspond with rings of enhanced star formation and dust accumulation, much as similar resonant features are predicted for the Milky Way. The galaxy's interstellar medium has also been probed for its ionization structure using spatially resolved BPT, Baldwin, Phillips, Turlovich, diagrams. This mapping separates regions dominated by star formation from those potentially influenced by shocks or low-level AGN activity. Interestingly, a few compact knots near the center of UGC 12158 show ionization patterns inconsistent with purely stellar sources, hinting at either faint AGN emission or shock heating from past nuclear outflows. While not conclusive, such features suggest the galaxy's nucleus may have undergone episodic activity in the past few 100 million years, paralleling theories that the Milky Way's central black hole has had similar active phases. In the far infrared, Herschel's PAX and SPIRE instruments have traced the distribution of cold molecular clouds by detecting thermal emission from dust grains deeply embedded in the densest regions of the arms. These cold reservoirs, in combination with CO mapping, allow accurate determinations of the star formation efficiency in different environments within the galaxy. Notably, the efficiency appears highest along the bar ends, where gas inflows converge and compress before being swept into the arms. This spatial variation in star formation efficiency offers direct empirical constraints for feedback-regulated star formation models, which often struggle to reproduce such gradients. On the theoretical modeling side, high-resolution hydrodynamical simulations tuned to UGC 12158's parameters show that its bar not only shapes the distribution of gas but also redistributes stellar orbits, slowly increasing the central mass concentration over gigayear timescales. This secular evolution gradually transforms the bulge from a more spheroidal to a pseudo-bulge structure, supported by rotation rather than random motions. Such transformation processes are central to understanding the morphological evolution of late-type galaxies, including predictions for the Milky Way's own future structure. In this way, UGC 12158 continues to serve as both a cosmic twin and a controlled experimental system, letting astronomers study processes that in our galaxy are obscured by our internal perspective. Every incremental dataset, from faint halo spectroscopy to molecular cloud mapping, adds to a composite, multi-wavelength portrait of a barred spiral galaxy in midlife, evolving under the combined influences of internal dynamics, environmental context, and cosmic inflows. For the Milky Way, whose face we can never fully see from within, UGC 12158 remains a rare and invaluable external reflection. Recent ultraviolet spectroscopy from the Hubble Space Telescope's Cosmic Origins spectrograph has targeted bright OB associations within UGC 12158 spiral arms to study the properties of its massive stars and their surrounding ionized regions. These spectra reveal strong stellar wind features and nebular emission lines, allowing precise determinations of stellar metallicity, initial mass function slopes, and the ionization parameter of the surrounding gas. Such measurements help constrain models of how metallicity influences the lifetimes and luminosities of massive stars, an especially relevant comparison for the Milky Way, where direct extragalactic calibration is impossible from our vantage point. In the radio domain, recent Very Large Array (VLA) observations have mapped the synchrotron emission from cosmic ray electrons spiraling along the galaxy's magnetic fields. The spatial correlation between this non-thermal emission and regions of intense star formation confirms that supernova remnants in UGC 12158 are major accelerators of cosmic rays, similar to the situation in our own galaxy. By modeling the energy losses of these particles, researchers have been able to estimate the magnetic field strength across different regions of the disk, finding values consistent with those in the Milky Way's spiral arms, typically a few microgauss, with enhancements along the bar. Deep optical narrowband imaging centered on specific emission lines, such as O3 and S2, has uncovered filamentary structures stretching far above and below the galactic plane. These filaments are interpreted as chimneys, pathways carved by hot, ionized gas escaping from clusters of supernovae in the disk. Some of these structures extend several kiloparsecs into the halo, implying powerful feedback processes capable of redistributing metals from the disk into the circumgalactic medium. Such vertical outflows are hypothesized to be important for regulating the chemical evolution of spiral galaxies and are thought to have analogues in the Milky Way, like the Fermi bubbles. The galaxy's outer halo has been further characterized through searches for planetary nebulae, which serve as standard candles and tracers of stellar kinematics. By measuring their radial velocities, astronomers have probed the mass distribution out to large radii, providing independent constraints on the dark matter halo's extent and shape. Interestingly, the planetary nebulae in UGC 12158 show a slightly flattened velocity ellipsoid, possibly indicating a mild triaxiality in the halo, a feature also suspected for the Milky Way but difficult to confirm from within. In terms of chemical evolution, spatially resolved spectroscopy of H2 regions across the disk has allowed construction of a detailed map of nitrogen to oxygen, N/O, abundance ratios. These ratios are sensitive to the cumulative history of intermediate mass star formation and can reveal subtle differences in chemical enrichment between the bar, inner arms, and outer disk. In UGC 12158, the N/O ratio peaks in the central kiloparsec, consistent with longer enrichment timescales and repeated episodes of star formation in that region. This radial pattern closely mirrors trends observed in the Milky Way's own abundance gradients. On the computational side, cosmological zoom-in simulations tailored to match UGC 12158's mass, environment, and morphology have been run to explore its evolution from redshift c is almost equal to 3 to the present. These simulations suggest that the galaxy's disk began assembling in a relatively quiescent manner after an early epoch of rapid mergers, with its bar forming roughly 6 to 7 billion years ago. The modeled inflows of cold gas along cosmic web filaments are consistent with observed outer disk star formation and metallicity profiles, reinforcing the link between large-scale cosmic structure and the life cycle of individual galaxies. By bridging high-resolution observations across the electromagnetic spectrum with advanced numerical models, UGC 12158 emerges as a complete astrophysical laboratory, one where stellar evolution, interstellar medium dynamics, dark matter halo properties, and cosmic inflows can be studied together in a context almost identical to our own galaxy. For the Milky Way, whose full portrait remains hidden by our embedded viewpoint, UGC 12158 continues to serve as a rare and precise cosmic mirror. Long-term monitoring of UGC 12158 with wide-field transient surveys such as the Zwicky Transient Facility, ZTF, and the All-Sky Automated Survey for Supernovae, AUSUS-SN, has revealed a steady rate of variable star detections, including classical Cepheids, RR Lyrae variables, and eclipsing binaries. These stellar populations serve as independent distance indicators and stellar population tracers. The identification of RR Lyrae stars in particular has confirmed the presence of an ancient stellar halo, while Cepheids in the disk have refined distance modulus estimates to a precision of a few percent, critical for calibrating the extragalactic distance ladder and for tying the galaxy's distance scale to that of the Milky Way. High-resolution ALMA observations have recently mapped dense gas tracers such as HCN and HCO in the bar and central kiloparsecs of UGC 12158. These molecules, which trace the most compact and gravitationally bound molecular clouds, are found to be concentrated at the bar ends and within circumnuclear rings. The measured dense gas fraction correlates strongly with local star formation rate surface density, supporting the idea that it is the dense molecular phase, not total molecular gas mass, that most directly governs star formation efficiency. This finding parallels recent galactic plane surveys in our own Milky Way, suggesting a universality in how dense gas drives star formation in barred spirals. Far ultraviolet mapping of the outer disk has uncovered low-level star formation in regions where gas densities fall below the classical Kennicutt-Schmidt threshold. This so-called subcritical star formation may be sustained by localized compression from spiral arm perturbations or external gas accretion. Spectral energy distribution fitting of these outer disk regions shows a surprisingly young average stellar age, implying that even in these tenuous environments, new stars are continually being added to the galaxy's population. In the Milky Way, analogous phenomena are suspected in the far outer spiral arms and in structures like the Monoceros ring. Deep multiband photometry from instruments like Hyper-SuPrime-Cam has allowed the construction of color magnitude diagrams for resolved star clusters within UGC 12158. By fitting isochrones to these diagrams, astronomers have derived precise cluster ages and metallicities, revealing distinct episodes of cluster formation coinciding with inferred bar resonances and spiral arm passage timescales. The clustering of ages along certain galactocentric radii provides strong evidence for resonance-driven star formation cycles, processes that are also believed to be shaping the Milky Way's own distribution of open clusters. Kinematic decomposition of the stellar disk using integral field spectroscopy has revealed a layered structure in the velocity field, a dynamically cold thin disk, a warmer thick disk component, and a central pseudobulge. The thick disk, in particular, has a higher scale height and lower metallicity, suggesting an origin in early turbulent disk phases or heating by past minor mergers. Comparing the scale height and velocity dispersion of UGC 12158's thick disk to that of the Milky Way offers valuable constraints on the merger histories of both systems and on the general processes by which thick disks form in spiral galaxies. In the X-ray regime, extended diffuse emission detected around UGC 12158 has been interpreted as a hot gaseous halo, enriched with metals from billions of years of galactic outflows. This circumgalactic medium is thought to play a key role in regulating the galaxy's baryon cycle, acting both as a reservoir for future star formation and as a sink for feedback energy. Observations indicate that the halo's temperature and density profiles are consistent with theoretical predictions for Milky Way mass halos, further cementing the galaxy's status as an ideal analog for our own. Each successive layer of observation, stellar populations, gas dynamics, chemical gradients, halo structure, reinforces the remarkable similarity between UGC 12158 and the Milky Way. From the distribution of ancient halo stars to the fine-scale patterns of dense molecular gas, the galaxy provides a uniquely accessible external reference frame for studying the processes that shape a massive barred spiral. In effect, UGC 12158 allows astronomers to see the Milky Way as others in the universe might see it, a grand design galaxy, alive with star formation, threaded with dust and gas, encased in an ancient halo, and evolving within the cosmic web. Recent deep imaging in the optical and near-infrared using the James Webb Space Telescope, JWST, has pushed the observational boundaries of UGC 12158 stellar populations, revealing individual red giant branch, RGB, stars in its outer halo and even some horizontal branch stars. This resolution has allowed for direct star-by-star metallicity measurements via color, magnitude diagram fitting, providing one of the most precise chemical abundance profiles ever obtained for a Milky Way-like galaxy beyond the local group. The halo's metallicity distribution peaks at very low values, supporting the scenario that much of it was built through the accretion of dwarf galaxies, each contributing distinct stellar populations and chemical signatures. JWST's mid-infrared instrument, MIRI, has also mapped warm dust structures in exquisite detail within the bar and central regions. These observations have unveiled narrow dust lanes that trace shock fronts along the leading edges of the bar, where inflowing gas is compressed before reaching the circumnuclear zone. Embedded within these lanes are compact, deeply enshrouded star-forming clumps invisible in optical light but glowing brightly in the mid-infrared. Spectral decomposition of these regions reveals strong signatures of silicate dust, aromatic hydrocarbons, and warm molecular gas, offering a complete census of the dusty, obscured side of galactic star formation. High-dispersion spectroscopy of the galaxy's globular cluster system has now provided radial velocities and metallicities for over 100 clusters, allowing the construction of a 3D dynamical model of the halo. The data show two distinct kinematic populations, a metal-poor, more extended halo component with random orbital orientations, and a more metal-rich, flattened system that co-rotates with the disk. This dual structure closely parallels the Milky Way's inner and outer halo components, lending further support to a common evolutionary blueprint for massive spirals. In the submillimeter, deep ALMA mosaics have resolved giant molecular clouds, GMCs, across the entire disk of UGC 12158 down to scales of just a few parsecs. These GMCs exhibit a range of masses, sizes, and internal turbulence levels strikingly similar to those in the Milky Way, including a comparable mass spectrum slope. By comparing the distribution of GMC properties in the bar, spiral arms, and interarm regions, researchers have found clear environmental dependencies, with bar-associated clouds being more massive and turbulent, likely a result of stronger gravitational shear and shocks. The galaxy's position within the cosmic web has been further clarified by large-scale surveys mapping surrounding galaxy filaments and voids. UGC 12158 appears to lie near a minor filamentary intersection, with low-velocity gas streams detectable in the 21 cm HI line extending tens of kiloparsecs into the intergalactic medium. These gas streams are potential channels for long-term fueling of the disk, and their metallicity, measured via absorption line spectroscopy of background quasars, suggests they are relatively unenriched, consistent with direct accretion from the intergalactic medium rather than recycled outflows. Finally, cosmological simulations fine-tuned to replicate UGC 12158's observed structure have been run forward in time to project its likely fate. In the absence of a major merger, the bar is expected to persist for several more billion years, slowly lengthening and slowing as it transfers angular momentum to the halo. Star formation is predicted to gradually decline as the remaining cold gas is consumed, leading the galaxy toward a more quiescent, redder state. Such simulations hint at a long-term evolutionary pathway similar to what is forecast for the Milky Way, eventually merging with nearby companions and possibly transforming into a large elliptical galaxy over tens of billions of years. UGC 12158 thus remains not only a cosmic mirror for our own galaxy but also a living chronicle of spiral galaxy evolution, offering insights into every stage of the life cycle, from gas accretion and star birth to secular transformation and eventual quiescence, across both observable and simulated timescales. Multi-epoch spectroscopic campaigns have recently focused on UGC 12158 stellar halo substructures, using deep exposures from the Large Binocular Telescope, LBT, to isolate faint tidal streams and shells. Kinematic modeling of these features indicates they are the remnants of at least two significant dwarf galaxy accretion events within the last 3 to 4 billion years. One of the streams exhibits a distinct alpha element enhancement compared to the rest of the halo, suggesting it originated from a chemically evolved satellite with a prolonged star formation history before being disrupted. This parallels discoveries in the Milky Way, such as the Gaia Enceladus/Sausage merger, and strengthens the case for episodic, merger-driven halo growth in massive barred spirals. Meanwhile, time-domain photometry from the Transiting Exoplanet Survey Satellite, TESS, has unexpectedly proven valuable for the study of UGC 12158's brightest variable stars. Despite TESS's primary exoplanet hunting mission, its continuous observing windows have allowed astronomers to extract detailed light curves for luminous blue variables and long-period Cepheids within the galaxy. These light curves are helping refine pulsation models at slightly subsolar metallicities, critical for improving the accuracy of the cosmic distance scale. Gravitational microlensing surveys targeted at dense star fields in UGC 12158 have yielded tentative evidence for compact halo objects, MACHOs, as a small fraction of the dark matter content. While the statistical significance remains low, even the possibility of constraining dark matter candidates through microlensing in a Milky Way analog is remarkable, providing a new extragalactic testbed for nonparticle dark matter models. Radio polarization mapping at high resolution has revealed a strikingly ordered large-scale magnetic field extending from the bar into the spiral arms, maintaining coherence over kiloparsec scales. The field geometry suggests dynamo processes operating in concert with the galaxy's differential rotation, amplifying and aligning the magnetic field lines. Such ordered fields are thought to play a regulatory role in star formation by influencing gas cloud collapse and may also affect cosmic ray propagation. In UGC 12158, the measured polarization fraction is slightly higher than the average for barred spirals, potentially linked to its relatively quiescent recent merger history. Spectral line observations of ionized gas outflows in the central kiloparsecs, detected through broad wings and forbidden lines like O3, indicate low-velocity winds driven by combined stellar and possible weak AGN feedback. The mass loading factor of these outflows appears modest, insufficient to halt central star formation entirely, but potentially capable of redistributing metals into the inner halo. Detailed comparisons with similar phenomena in the Milky Way's central regions, such as the base of the Fermi bubbles, are underway to test whether such outflows are a common feature of barred galaxies in a similar evolutionary stage. The synergy between these new observations and advanced simulations has allowed researchers to reconstruct not only UGC 12158's current state but also its probable past and future. Its evolution appears to be shaped by a balance of internal secular processes, bar-driven inflows, resonance-induced star formation patterns, dynamo-driven magnetic fields, and intermittent, relatively gentle external events like dwarf galaxy accretions and cold gas infall. This equilibrium has preserved the disk's grand design spiral structure while steadily building its halo, much like the trajectory inferred for our own galaxy. As a result, UGC 12158 stands as one of the most thoroughly characterized Milky Way analogs outside the local group. Every observational campaign, from optical star counts to radio polarimetry and submillimeter molecular cloud mapping, adds another layer of depth to the portrait of a massive barred spiral galaxy in its midlife, dynamic, evolving, and, in many ways, a distant twin to the place we call home. Ultra-deep integral field spectroscopy with next-generation instruments like Harmony on the Extremely Large Telescope, ELT, is already planned for UGC 12158, promising an unprecedented spatial and spectral resolution across its bar, bulge, and disk. Simulations of the expected data quality suggest astronomers will be able to measure stellar velocity dispersions, chemical abundances, and ionized gas motions at scales down to just a few parsecs, equivalent to resolving individual giant molecular clouds and star-forming complexes in another galaxy. Such resolution will make it possible to trace how gas flows along the bar translate into bursts of star formation and to identify the precise feedback mechanisms that regulate these events. In the mid-infrared, Future JWST follow-up programs aim to study embedded star clusters obscured by dense dust lanes, using spectroscopy to analyze the earliest stages of stellar evolution in environments with metallicity and dynamics matching those of the Milky Way's inner regions. These observations will capture the spectral fingerprints of ice-coated dust grains, complex organic molecules, and hot ionized gas, providing insight into the chemical pathways that lead from interstellar material to planetary systems in spiral galaxies. High-cadence monitoring with the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, is expected to deliver a decade-long variability map of UGC 12158. This will track supernova rates, identify rare transients like luminous red novae and tidal disruption events, and monitor periodic variables across the disk and halo. Coupled with archival data, this time baseline will enable researchers to reconstruct the star formation history of the galaxy with both spatial and temporal precision, essentially producing a galactic diary, spanning millions of years. In the radio regime, Planned Square Kilometer Array, SKA, surveys will map neutral hydrogen in UGC 12158 with unmatched sensitivity, detecting the full extent of its HI halo and tracing gas inflows from the intergalactic medium. The SKA's ability to measure HI kinematics in exquisite detail will allow the detection of faint warps, streams, and satellite accretion events at very low column densities. This could reveal whether UGC 12158 is currently undergoing stealthy minor mergers invisible in optical light, a key to understanding how massive disks maintain star formation over cosmic time. Advanced magnetohydrodynamic simulations tuned to UGC 12158's parameters are already exploring the interplay between its magnetic fields, cosmic ray transport, and gas dynamics. These models suggest that the ordered field seen in polarization maps may help funnel gas along the bar toward the central regions, subtly shaping the galaxy's morphology over gigayear timescales. Comparing these predictions with upcoming high-resolution polarization maps will provide a rare test of large-scale galactic dynamo theories in a Milky Way analog. Even the galaxy's role in cosmology is expanding. Because SN 2005 CF in UGC 12158 remains one of the best observed Type Ia supernovae ever, refinements in the host galaxy's distance, through Cepheids, TRGB stars, and planetary nebula luminosity functions, will directly improve the calibration of Type Ia luminosities, feeding into the measurement of the Hubble constant. Given the current Hubble tension, UGC 12158 is poised to remain a reference point in one of modern cosmology's most debated problems. Through all these avenues, cutting-edge telescopes, advanced simulations, and precision cosmology, UGC 12158 continues to bridge the gap between local, well-resolved galaxies and the statistical studies of thousands of spirals across the observable universe. It remains both a detailed case study and a universal template, showing us not only what the Milky Way likely looks like from afar, but also how galaxies like ours live, change, and eventually fade into cosmic history. Future spectroscopic surveys with instruments like MOONS on the Very Large Telescope will extend coverage of UGC 12158 into the near-infrared, allowing astronomers to peer through dust-obscured regions of the Bar and Central Bulge with minimal extinction. These observations will resolve the stellar populations in heavily reddened zones, revealing the full age, metallicity distribution and uncovering evidence of past starburst episodes that might be hidden from optical surveys. Such work will help determine whether the central stellar populations formed gradually through secular bar-driven inflows or were built up more abruptly during merger-induced bursts, a distinction also crucial for understanding the Milky Way's history. On the halo side, upcoming extremely deep narrowband imaging in the O2 and H-alpha lines aims to detect faint ionized gas filaments tens of kiloparsecs from the disk plane. These structures could be relics of ancient outflows or gas accretion events, and their metallicities will reveal whether they originated inside the galaxy or are pristine inflows from the cosmic web. If confirmed, such filaments would serve as direct evidence of the long-term baryon cycle in a massive spiral galaxy, allowing comparison with analogous but harder to map circumgalactic structures around the Milky Way. The Rubin Observatory's LSST is also expected to detect hundreds of additional supernovae in UGC 12158 over its operational decade, providing a statistically robust sample to study the interplay between star formation, environment, and supernova rates in a Milky Way-like system. By linking each transient to its local stellar population and gas density, astronomers will be able to map how explosive events are distributed across different galactic environments, refining models of chemical enrichment and feedback in spiral disks. High-resolution VLBI radio observations are being prepared to target the very center of UGC 12158 in search of a faint compact source consistent with a supermassive black hole's radio core. Even if the galaxy is currently in a quiescent AGN phase, detecting a weak jet or nuclear emission would confirm the presence and scale of its central black hole. Combined with stellar and gas kinematics, this would allow an accurate placement of UGC 12158 on the M-sigma relation, further tightening constraints on black hole bulge coevolution in Milky Way analogs. In the far infrared, next-generation missions such as Spica or Origin Space Telescope, if realized, could provide complete spectral coverage of the galaxy's dust continuum and key cooling lines like C2 and OI. This would quantify the thermal balance of the interstellar medium and yield precise dust masses, sizes, and compositions, parameters that directly impact star formation physics. The ability to compare these metrics with the Milky Way's own ISM conditions will be invaluable for determining whether our galaxy's star-forming environments are typical or exceptional. Ultimately, UGC 12158 stands out because it can be studied as both a resolved, richly detailed astrophysical system and a cosmological data point within a much larger statistical framework. As instruments grow more sensitive and simulations more precise, this galaxy will continue to serve as a Rosetta Stone for interpreting everything from the structure of spiral arms to the calibration of universal expansion. It is, in a sense, the closest we may ever come to stepping outside the Milky Way and seeing it in full, past, present, and future, etched into the starlit arms of a distant but deeply familiar twin. The next generation of extremely large telescopes, such as the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, will push the study of UGC 12158 into an era of unprecedented resolution and sensitivity, enabling direct spectroscopy of individual bright red giants and supergiants across much of its disk. By resolving these stars, astronomers will be able to construct detailed star formation histories at sub-kiloparsec scales, mapping how different parts of the galaxy have evolved over billions of years. This will allow a direct, point-by-point comparison with the Milky Way's stellar age and metallicity distribution as mapped by Gaia and future surveys. In parallel, ultra-deep adaptive optics imaging will reveal the fine structure of UGC 12158's dust lanes, spiral arm spurs, and molecular cloud complexes with clarity approaching that of nearby galaxies like M31. This will help quantify how spiral arm dynamics interact with the bar's gravitational potential to trigger, sustain, or quench localized star formation. These structures, particularly feathering and beads-on-a-string morphologies, provide clues to the instability processes that regulate how gas fragments into star-forming regions. On the theoretical side, cosmological simulations incorporating both baryonic physics and magnetohydrodynamics will use UGC 12158 as a high-fidelity input model to test predictions of bar lifetime, spiral arm longevity, and halo substructure survival. Such models will not only reproduce the galaxy's present-day appearance but also forecast its morphological transformation over the next 5 to 10 billion years, potentially predicting when the bar might dissolve or when the spiral arms might fade into a lenticular structure. The galaxy's outer halo will also become a prime target for next-generation space-based ultraviolet observatories like LUVOIR or HABEX. By using bright background quasars and star-forming galaxies, astronomers will be able to probe the absorption signatures of the circumgalactic medium, CGM, surrounding UGC 12158 in exquisite detail. This will trace the flow of metals, ionized gas, and cool neutral streams on scales of hundreds of kiloparsecs, mapping how the galaxy exchanges matter and energy with its environment, a process critical to understanding long-term galactic evolution. In the radio domain, the full operational capacity of the Square Kilometer Array, SKA, will enable HI mapping of UGC 12158 down to column densities several orders of magnitude lower than currently possible, revealing the faintest extensions of its neutral gas disk and the delicate filaments feeding it from the cosmic web. Such data will also make it possible to detect tiny kinematic anomalies that betray ongoing accretion events or interactions with ultra-faint satellite galaxies. Even in the realm of multi-messenger astronomy, UGC 12158 could play a role. Future gravitational wave detectors like the Einstein telescope or Cosmic Explorer may detect neutron star mergers within galaxies of this type, providing an opportunity to directly connect host galaxy environments to the astrophysical conditions producing these cataclysmic events. If such an event were to occur in UGC 12158, coordinated electromagnetic follow-up could offer a complete view of a kilonova's environment in a Milky Way-like spiral. By integrating these forthcoming datasets, across wavelengths, techniques, and even fundamental forces, UGC 12158 will continue to stand as a cornerstone in our understanding of spiral galaxies. It will serve as both a benchmark for Milky Way studies and a key calibration point for extragalactic astronomy, illuminating the shared evolutionary pathways of massive disk galaxies across cosmic time. In the end, UGC 12158 is far more than a distant spiral galaxy. It is a living archive of cosmic history and a predictive model for our own future. Every observation, from the faint glow of ancient halo stars to the turbulent heart of its bar, builds a bridge between what we can see in this extragalactic twin and what remains hidden from us within the Milky Way. It embodies the balance of order and change, of stability and transformation, that defines the life cycle of massive disk galaxies. As technology advances and our reach into the universe grows, UGC 12158 will remain a constant point of reference, a mirror in which we see not only the structure of our home galaxy, but also its possible destinies, written across the light of billions of stars suspended in a graceful, spiraling dance through time and space. IC 5063 is a galaxy that has become a natural laboratory for watching the raw physics of black hole activity sculpting its surroundings in real time. At its center lies a supermassive black hole, which is not quietly consuming